First class this morning, something like 20 some odd students supposed to be in it. I had 2 at the beginning of class. Yeah, more came in later, so we wound up with a reasonable sized class. Then my second class was supposed to have 5 in it. 0 showed up. The next one, 3 in it. 0 showed up. So I'm glad to see somebody here today, so I'm glad y'all are here. Hopefully some more will be coming, especially since we have a lab today. So we are now recording. Let me say this, and as Siegfried mentioned, the bad news, sorry about this, folks, there's no school next week. College is open Monday, Tuesday, and Wednesday, but there are no classes. We have professional meetings. Some of them will be going down to Montgomery for those meetings. Others of us will be on campus here for our meetings, but it's probably not going to be on this campus. I haven't seen the schedule yet, but usually they're on the Birmingham campus. So Monday and Tuesday, if you're looking for me, I probably won't be on this campus. I'll probably be on Birmingham. Wednesday, they count a duty day, so I will be one of the 2 campuses. I'll find out tomorrow if I can get enough done tomorrow that I don't need to come back out here on the following Wednesday. Then I'll just go to Birmingham then too. But I might need to come here to take care of some sort of business. So I'll be on one of the other campuses. If you need to see me Wednesday, call, okay? My same number works on both campuses, and if I'm there, I'll answer. If it's early in the day and I don't answer, try again in 15, 20 minutes just to see. I may have been out of the office for a bit. So try again. If after repeated tries you don't get me, that means I may have taken personal leave. I don't know. So, but before I go any further there, I just received the second paper that's been turned in for this class out of, 17 students or something like that. Not a good number, okay? I'm glad those 2 are in. Please get those. And this Thanksgiving break is one of your last best chances to have a concentrated amount of time to work on the paper. After we come back, it's going to be hectic. We got finals coming up. You have projects and papers and other things and other courses, tests and stuff coming out your ears. So don't let the break go by without working on your paper. You may not finish it, but at least get going on it. Okay. Another thing, the first lab. I still have 1, 2, 3 people haven't turned in the first lab. The first test, I think one person hasn't done the first test. You. Second lab, 1, 2, 3 people haven't turned in the second lab. Not always the same 3 people, by the way. The third lab, barely half the people have turned that in. The fourth lab, missing 1, 2 there. Now the second test, everybody has finished, and I turn them back. Have any of you not received your second test? Okay, let me get that because I can return those to you. They have been turned in. Didn't get deep enough. Okay. Test 2. Yep. Tiffany's not here yet. James not here yet. Tristan. Michael's not here yet. Patrick's not here yet. Philip. And Amita's not here yet. So here's your test 2, those of you who are here. All right. So test 2. You've got back those who have been here, okay? I am recording, so good. That was test 2. Lab 5, barely half have turned in lab 5. Lab 6, probably about the same. And lab 7 we did last time, and several people turned that in. We're still missing several. Test 3 we did last time. I don't have all those graded. That's what I'll be working on while y'all are doing the lab tonight, and tomorrow while I'm on Birmingham campus. So there's please try to get those things caught up. Any questions before we get started on today's class? Okay, we've got the slideshow set up. I'll do it from current slide. And this is where we left off last time. Now, for those who weren't here, let me go over quickly part of what we did. There are 3 different types of heat flow. Okay, now, as I mentioned before, heat doesn't really flow, but it's a good name for it, a good verb to describe it. That comes from the old days when they actually thought heat was some sort of fluid that resided in materials. So that's why they call it heat flow. Well, it really doesn't flow, but it's a good way to look at it. The first of these was conduction. Conduction happens best in solids, okay, where you have fixed lattice rigid structure there. That's where it happens best. Even better is when you have free electrons to carry that heat. That's why metals are your best, very best conductors. Not just of heat, later we'll find they're true of electricity as well. Okay? So it works best in solids, somewhat in liquids, very little in gases. Okay? Then the second of these is convection, and that's the one we're starting with today. All right, now what is convection? Convection is energy transfer through the bulk motion of hot material. And I know that all of you have seen this happen before, and you probably felt it happen before as well. But if you ever have watched a pot boil, either looking down at it, but in the old days, and this isn't all that old days, they had this glass cookware called visionware. Does anyone remember that? It was sort of an amber-colored pots you could actually see through and watch them. And if you had watched that, you would see that the hot, usually on the eye of the stove, the center is the hottest part, but the sides of the pans are the coolest. And you could literally watch the water come up from the center where it was hottest and move out to the sides and then back down again. That was convection. That happens in rooms. It happens in buildings. It happens just about everywhere. I can remember the early school I went to, in grammar school and the early junior high, they had the old radiators that sat by the windows. Now, they made lots of noise as the water and the steam and the heat popped through the pipes and stuff, but really there were no moving parts except for the steam or water flowing through them. What happened was the cooler air at the bottom of the floor went up through the radiator, those veins they had in it, heated up, and then moved to the top. Okay? And that was what happened there. My great aunt and my grandmother's old houses, neither one of them standing anymore, they had floor furnaces. They had, I think it burned some type of oil, and the furnaces were down beneath the floor. There was a big grate on top, and the heat came up from the furnaces and warmed the house that way. Okay? When I moved to junior high my family moved to the next town south and went to a different school. In that one, actually, they had heating coils in the floor, and they just would heat up, and the room would heat up that way. Convection was how that was happening. The bulk motion of hot material. They mentioned space heaters here, gas furnace. Now, I don't like that they say forced. To me, that means a forced air furnace. Then you're blowing it around, okay? The old gas furnaces that just sat underneath the floor and when the heat rose, that's the example of convection. Space heaters, now if the space heater has a fan in it, that's not convection. I mean, it's partly convection, but if the space heater is just heating up, and we've had some of those too, typically the house we're in now was built in the 1930s. Later, someone converted it to, heating, air conditioning, within the house. Back when it had coal fireplaces in them, and it probably was a pretty chilly old house then, but it already had whole house conditioning by the time we bought the house. But the bathrooms didn't have any vents in them. Well, one bathroom, our bathroom, the master bath, didn't have a vent because they had made the master bath out of parts of 2 bedrooms, and neither one of those had a vent in it. The other one did, but the vent actually there was right in the shower, and you didn't like to have the air blowing on you there, but we didn't use that much, so we didn't use that. So we had space heaters in both bathrooms, and originally we had them just that were radiant heaters, and it went by convection. The one we have now has a little fan in it, so it's not exactly convection. But how this works is natural convection mechanism. What happens when any material heats? It expands, exactly. And the reason for that, especially if you're talking about air, and by the way, time out on this, convection works hardly any in a solid. There just is no convection within a solid because things can't move that much. But in fluids, which includes liquids and gases, that's how convection works. That's where it works. They don't do conduction well, but they do convection extremely well. So here's what happens. When you heat up a material, fluid, whether it's a gas or a liquid, the molecules tend to, when you heat it up, temperature rises, the average kinetic energy of the molecules increase. That means they're bumping into each other more frequently and more energetically, so they bump further and further apart. So that makes for an expansion. Now that happens in solids, the expansion, but you don't have convection in solids. You do in fluids, liquids and gases. In that water in the pot and the air in the room, the hot air rises. That's why on the old radiators, when it heated it up, the hot air was less dense and it went up, and the cool air came around underneath. That's convection, okay? That's how chimneys basically work. You burn the material, wood, coal, whatever you're burning in the fireplace, and the hot air goes up. So really with a fireplace, most of your heat's going right up the stack. There's some heat that goes radiated out of the fireplace, but most of it goes straight up. That's why wood stoves that have the pipe inside the house, you're getting up extra heat out of that as well. And especially if the wood stove, it has to go through a circuitous route to get to it. Quite often that's really fairly efficient heating, okay? Hot air rises. Here's the example of the old radiator. The cool air comes down under it. The heater is sitting here. The radiator is sitting here. Lots of these veins here for the vent, for the air to go through. Holes this way too. And as it goes up, it heats the air. The air molecules get further apart, less dense. They rise. The cooler air comes down. That's how a radiator effectively heats a room. Those people sitting closest to the radiator might be burning up, while these people over on this side might be still a bit on the chilly side. Okay. Now, here is that principle of hot air rising. By the way, in buildings and houses and things like this, sometimes that's called the chimney effect. That's why I mentioned fireplaces and chimneys, because, for instance, the house we lived in on the farm in Georgia, my father put in a wood stove in the basement. And what he'd do is get that thing cranked up really good, open the stairwell door, and the heat came up the stairwell and really heated the whole house, okay? Bedrooms, kitchen, living area, any of the areas, and the cool air came down the stairwell too, and it just kept circulating. We had backup heat too, but he was keeping that running pretty good. So here's how it worked. When you start off, 2 blocks of air, now, they really aren't blocks of air, but you can imagine them as being an invisible boundary here. And these blocks, if they're the same size, they contain the same number of molecules. Okay? Now, If you heat up this side, the molecules spread and become further apart. Well, if they're still contained in the box, you still have the same molecules in the box. But if you had an equal volume, which is really what you have, this equal volume then would have fewer molecules. Because all these same molecules are in the big box. If you had a smaller box, you obviously would have fewer molecules. So now you have the colder air sinks, the warmer air rises. To me, a little dorky kind of example, but it does tell the picture, tell the story. Okay? So any question on convection? What materials does it work best in? Which phases of matter? What we call fluids. That's liquids and gases. Okay? And conduction happens best in solids. The third type of heat flow is radiation. I've already used the term at least once today. But if you think about it, this is a very popular form of heat flow. Where do we get most of our heat from? The sun. Okay, what's between us and the sun?
Atmosphere.
Okay, atmosphere is a little thin band of gases that surround the Earth. And what? Space. No solids, no fluids. How is the heat getting to us from the sun? Radiation. Radiation is the energy associated with electromagnetic waves. They can operate in a vacuum. In fact, they operate best in a vacuum. You can have radiated heat in air. We always do. For instance, I mentioned those little space heaters that didn't have fans on them. Some of them had a reflective surface in the back, and that radiated heat. You could stand right in front of it and feel the heat right there, but then also convection was happening as well. Okay? So it operates best in a vacuum, like space. Now, space isn't a total vacuum, but it's close enough, about as close as you can get to an absolute vacuum. That's where radiation works best. Does okay through our atmosphere, but not completely. Thank you very much it doesn't, because some of the radiation that gets blocked by our atmosphere, why we're able to live on the planet, is because our atmosphere blocks most of the deadly radiation, gamma radiation, X radiation, cosmic radiation, all that really high energy, deadly radiation, our atmosphere blocks it. I think someone may have mentioned the ozone layer. That's part of what it does. The ionosphere blocks a lot. Our whole atmosphere blocks that heavy. It only really allows through it this little spectrum of radiation called visible light. Now, a little bit more comes through. Okay, but visible light does come through. That's red, orange, yellow, green, blue, indigo, and violet. The 7 colors of the visible spectrum. Now, on the violet is the highest energy there. Just above that is what we call ultraviolet. Some of that makes it through our atmosphere as well. What's the results of that? Ultraviolet radiation. Okay, you got it. Okay, that's why some of us will tan somewhat, because the ultraviolet radiation is bombarding our body, and our body is trying to keep it from harming us, so it emits beta carotene, which tries to block it. And the more beta carotene comes to the surface, the darker the tan you've got. Some of you have a naturally high amount of beta carotene, so you typically aren't as likely to get skin cancers as those of us who are more fair complected don't have as much beta carotene. You're lucky. We're not. And I've already had one small skin cancer removed, and this is precancerous here, so I put sunblock on it every day. Summer, winter, spring, and fall, every day I have to put sunblock to keep it from turning into cancer. So you're absolutely right. Skin cancer is one thing that ultraviolet light causes. Okay? Yeah, watch that head. It'll come there too. I have to watch mine. I wear a hat just about always when I'm outside. Okay. The other things that come as a result of that, if you live long enough, the odds are you're going to get cataracts. I've had a cataract removed from this eye. The one in this eye isn't bad enough for them to remove it yet. But if you live long enough, ask your grandparents, the odds are they've had cataracts removed. Or they've got them now, and at some point they're either going to have them removed or live with them, you know. And that's why in the old days, if people lived long enough, they usually went blind because of cataracts. What that is, ultraviolet radiation hitting your lenses and the cornea of your eyes, and that's trying to protect from the inside the sensitive stuff, so they cloud up, and that's the result. Okay, so that's going to happen too. So radiation, our atmosphere blocks the most harmful part. Some ultraviolet gets through, but then the visible spectrum is all good stuff. That's what makes trees have photosynthesis, that kind of stuff. But there's also on the low energy but long wavelength, there is infrared radiation. Now we really don't get much of that from the sun directly, but this visible light that comes in, if you were sitting over here in the light here, I can feel it right now. I can feel heat. How is that heat reaching me? Radiation from the sun. But it's not the visible light that's warming me up. It's the visible light, when it comes through that glass, it lengthens the wavelength a little bit and makes it into what we call infrared radiation. Red is at the low end of the scale. Below that is infrared. What kind of structures do horticulturalists build and use? Second? Greenhouses, exactly. And the whole principle there is light comes in, the wavelength lengthens up, and therefore it's infrared radiation, and it keeps plants warm even in the wintertime as long as you've got a nice sunny day. But overnight and in cloudy days, you might have to add a little heat to it, but they're well insulated most of the time to try to keep the temperature fairly constant. Most of you probably recognize this. If I were to go out there to my vehicle right now and get in it, it's going to be, I'm going to guess, close to 5 to 10 degrees warmer than the air is. Why? The light has come in the windows, lengthened to infrared radiation, heat, and that has warmed it up. The greenhouse effect. Where have you heard that lately? Second? Global warming, exactly. That's what is happening. I mean, thank you, our atmosphere is there to do it. It's always there. We are far enough from the sun that we really should be too cold to support life. But because of our atmosphere trapping the heat as infrared radiation, then we're able to maintain a relatively stable, comfortable, life-supporting temperature. Don't get too hot to kill things or too cold to freeze things, so we generally pretty good. However, the greenhouse gases, they call them, are largely those who contain lots of carbon. Two of those in particular, carbon dioxide and methane. Okay? There are other greenhouse gases, but those are the two that contribute the most. And where do we get carbon dioxide? Second? Okay. Any kind of emission where we have burning hydrocarbons, that's petroleum, coal, those kind of things, or carbohydrates, that's what we do. So every time we breathe out, we're breathing out carbon dioxide. Now, not enough to cause the atmosphere any major problem. Tiffany's here. Good deal. But in the last, I'm going to say about 200, maybe 250 years or so, we've had what we call the Industrial Revolution. And in that time, we have emitted more carbon dioxide probably than any other time before the Industrial Revolution. If you think about we started out burning lots of wood, that produces some carbon dioxide, but it wasn't enough to make a huge amount of difference. But when we started burning coal, petroleum products, and those kinds of things, the carbon dioxide levels have steadily been going up. I don't know the exact time frame. I'm saying 200, 250 years. And the more they've gone up, we've also watched our ambient temperature go up. Not very fast, very, very slowly. In fact, less than 2 degrees Celsius since the Industrial Revolution began. Okay? But that's still enough that we are losing glaciers. We are melting ice. In fact, does anyone remember the title of a book that Ernest Hemingway wrote about a famous mountain in Kenya, or Tanzania, Kenya? The Snows of Kilimanjaro. Kilimanjaro is the highest mountain on the continent of Africa. And even though it's very close to the equator, it had glaciers on it because it was so tall. You go to Kenya, Tanzania now, you will not see a single glacier, I don't think, or maybe just remnants. There is no more snow on Kilimanjaro, okay? He wrote it back in the, I think, 1940s. Since the 1940s, every glacier pretty much is melted off Kilimanjaro.
So global warming is not a hoax?
It's not a hoax. No, it isn't. Sorry, I could get sent to jail, couldn't I? I'm sorry.
Yeah, but hasn't the planet been overheating and cooling down and overheating and getting really frozen over thousands of years?
Okay, yes, it's been through these patterns. It's been through these patterns. The ice ages were the really cold times, and then in between they were much warmer. And then, yeah, that's happened. But that cycle, I mean, we're in the cycle now since the last ice age, and when was that? Hundreds of thousands of years ago, I think, or something like that, at least tens of thousands of years ago. So, but we're witnessing faster change now than happened back then. Those things happen very slowly over literally thousands and thousands of years. Now we're seeing it happen much more rapidly. And we're seeing the carbon dioxide concentration going up much more rapidly. I know there's a big bunch of controversy about it, and I bet you some of you are on both sides of the controversy. But when you look at the science, the numbers of it, that gradient is steeper. In fact, we were in a cooling period, expecting cooler temperatures to happen, but the global warming has turned that around, which wasn't a bad thing at the time it happened, but it's continued to happen, and it's beginning to be a little bit on the dangerous side, I think, okay, because it's happening so fast. And the trouble is that the contributions we've been making has been over about 200 to 250 years to get it to the point now where it's happening fast enough that we can't really control it. How are we going to stop that? We can't do it like that. We're going to have to slow down gradually, and it's still going to keep going up. Whether we are past the point where whatever we do can slow it down enough to ameliorate the effects of it, we don't know. We are awfully close to the point where we don't know if we can actually stop it or not. Okay? So it is scary. It is, to me, very scary. Okay? And that's what they mentioned down here, global warming. So let's go back up and catch this. All objects emit and absorb radiation. Okay? My wife says in the summer she doesn't like to sit too close to me because I'm just emitting too much heat, and probably thank you, cold weather, for coming. She'll sit a little closer to me. No, just kidding. Not to. But anyway, all objects emit and absorb radiation. Sometimes we call that black box effect. A black box will absorb heat, but it'll also emit heat. Okay? The temperature determines the temperature, average rate of the average kinetic energy of the molecules, the emission rate, how fast that's being emitted or absorbed, okay? The intensity of the emitted light. Now suddenly they went from radiation to talking about light. Well, that's exactly what is happening in an incandescent light bulb, okay? You're heating up that little filament of titanium so hot that it begins to glow, okay? So the temperature, how hot it is, determines the intensity of that emitted light, okay? If that's what you're doing. It also determines the type of radiation given off, okay? The temperature does. If a low, when they're studying stars out there, they look at the emission spectrum, and the type of radiation tells them about the temperature of the star. I mean, they're really good at it, at picking that stuff out. The temperature is determined by the balance between the rates of emission and absorption. If we're emitting as much heat as we're absorbing, the temperature stays about constant, fairly stable. If we're emitting more than we're absorbing, the temperature is going to decline, okay? But if we're absorbing more than we're emitting, then we tend to be going up. And that's what global warming is about. We emit more carbon dioxide into our atmosphere. That traps more of the infrared and keeps it from going back out into space. So now we become a heat sink. More radiation comes in than is leaving, and we can't sustain that indefinitely. Otherwise, the temperature will gradually go up. In our lifetime? No. Not even in your children's lifetime, probably. But at some point, things can happen. And guess what? It's just not going to get hotter. I was hearing, actually there's a movie out now called After the Flood, I think it is, okay? Leonardo DiCaprio narrates it, and he's in it. It's not a fictional movie, it's real, it's nonfiction. And he goes all over the world looking at some of the various things going on. And one of the scientists he talks with, and this scientist has absolutely no horse in the race, because he's got, if I understood it right, he has a form of pancreatic cancer, which is not curable. And he's basically living out his last few years of his life doing all he can to study and make this knowledge available to everyone. And he shows just incredible statistics on this. And what he was, I think he was the one that was saying, what's going to happen is as we melt the polar ice caps and all that, and the glaciers and that kind of stuff, all that cold water goes into our ocean. And actually what's going to happen, okay, two things are happening. Number one, the sea level is rising. And there's already island countries in the Pacific and other places that people who used to live on the beach have had to move inland because the beach is following them in, okay? Their houses are now partially underwater. Where the houses used to be, they cannot live there anymore because of Venice, Italy. What is Venice, Italy known for?
Being on the city on the water.
Okay, it's a city on the water, and I've been to Venice twice, and there aren't many cars in Venice. Everybody travels by boat because they have all these canals and stuff. You walk over bridges and stuff. There are no cars there because it's a series of islands and other things all connected into one city. Beautiful place, and already most of the ground floors there are now basement floors, and they're somewhat underwater. It is. The water, sea level is rising. Ever so slowly, but it is rising. Okay? But that's just one effect. The second effect, that ice that's melting goes into the ocean, and that is actually going to drop the temperatures of the ocean. Okay? Now, the upper parts, the poles of the earth, are basically the air conditioners for the earth. The air that blows over them cools, and that blows down, and that keeps us from getting too hot. Well, what's going to happen as the ice melts, you're going to have less of that cooling effect. It's going to get colder up here and hotter down here. So the tropical regions are going to conceivably get so hot it can't sustain life, or at least comfortable life, very well. And the northern climates are going to get so incredibly cold it can't support life very easily there either. So people are all going to start then migrating to the middle, and the temperate regions are going to get overpopulation. You talk about refugee crises, those are going to be really bad because everybody's going to be trying to get to a more comfortable place. So things could get pretty bad, okay? So if you get a chance, I recommend see the movie. You can make your own decisions about it. You may not buy it all. You may not buy any of it. See the movie. It's worth the movie. I think it's after the flood. It's something about the flood. It's either before the flood or after the flood. I think it's after the flood is the title of it. Really well done. All right. Get off that horse, okay? All right. Convection and radiation. Now we're moving to the next big section, 4.4, which is energy, heat, and molecular theory. I thought we'd been there already. We've been talking about energy from the beginning of the chapter. We've been talking about heat from the beginning of the chapter. And we've been mentioning molecular theory from the beginning of the chapter. But here we're going to make a little bit of a break and a change of direction here. There are two responses of matter to heat. Okay? Most of the time when you add heat to a substance, what's it going to do? The temperature is going to go up. But not always. In fact, this is part of what's happening, as I said, to go up the ice cap. Okay? The first of these, temperature increase within a given phase. Now, what do we mean by phases? What are our three basic phases? Solids, liquids, and gases. So if a material, a gas, a solid, a liquid, within one phase, you add energy to it, the temperature is going to go up within the phase. Heat goes mostly into internal kinetic energy because guess what? That is what temperature is measured. The average kinetic energy of the molecules, that's what produces the temperature. Well, if you're all in the same phase, they used to say state, phase, then you're just increasing that kinetic energy and the temperature goes up. Okay. In that case, we use that equation that we had that dealt with specific heat because that has in it delta T, change of temperature. So you use your specific heat to measure how much the heat is increasing or how much the temperature is increasing. Okay? But the second possibility here, I'm sorry, we're going to do the graphic on them. Actually, this graphic is better after the next point, but we'll go and do the graphic now since we're here. Okay, when you have ice, you can have ice that's very, very cold. In fact, most of the time when you take the ice out of the freezer, does it melt in your hand immediately? No, in fact, sometimes it actually freezes to your hand. If you're, second, it does, and the reason is if you have a little bit of moisture on your hand, whether it's your hands were wet when you reached in there, or you're sweating a little bit, you reach in there, it actually freezes to your hand. It freezes that water that's on your moisture that's on, and that's why it sticks to your, and you can be in pretty serious problem there if it's very well stuck. Let me put it that way. Did any of you do you watch at Christmas time that movie, I think it's A Christmas Story? Do you know which one I'm talking about? Say that again? Yes, exactly, that one. Okay?
Yes.
It does. Okay? Now, it's extremely cold outside. You just have to keep pumping the warm water on it. But that was a movie. But the odds are it's happened before. But let me tell you, I wish he were here to hear it because it would embarrass him like crazy. My wife's brother, who's about 4 years younger than her, he is this Mr. Cool. I mean, he was a jock. He was a basketball player in high school and in college, and he's just dark hair. I mean, he just hasn't made. But he was a kid. Now this really happened. His mom had taken him and his younger sister, Karen wasn't there, to the grocery store. She was buying the groceries for the week or whatever. And Keith and Terry, or I think Terry was with her, but Keith had run off somewhere, which wasn't at all abnormal. And that she was getting ready to leave, and she said, "Terry, where's Keith?" She said, "I don't know. He was back there somewhere." So anyway, she went back. She said, "Go find Keith. We need to leave." So she went to find him, and there was Keith bent over the freezer portion of the, there in the grocery store. Cold food, frozen food, open container. And it had been a really hot day, and he thought that frost that had built up on that looked so cool, so he went to lick some.
Oh my God.
And he got his tongue stuck on the frost in the cooler. They were sitting there, and she said, she went and said, "Keith, come on, Mom's ready to go." Yeah. Look at Mom. Go get Mom.
Yeah.
And so Terry went and got her mom and brought her back there, and her mom was so terribly embarrassed. There his tongue stuck right next to the frozen food. She thought they were going to get in trouble. So she said, "Keith, come on." She grabbed him and left part of the skin of his tongue there. Blood started coming out. Put something over his mouth and got him out of the store as soon as possible. She was so, it was bad. So it really does happen. Okay.
Oh my God, I thought it was painful.
Okay. So
she
when,
was good.
yeah, I know. But anyway, if you have ice cold enough, you add heat to it, it just rises in temperature. If you have water that's not too hot, you add the heat to it, add energy to it, it's just going to change temperature. And if you had steam, okay, water in the vapor state, add heat to it, it just gets to be what they call drier and drier steam. In fact, they call it superheated steam. When they're running the turbines down wherever they are, now I'm not talking about the hydroelectric turbines, that works the same way, but when they're doing steam turbines, as in they burn coal, or they burn natural gas, or whether they had nuclear providing the heat, that steam is very, very hot. It becomes steam at 212 degrees Fahrenheit, which is 100 degrees Celsius. But they have this steam probably in excess of 500 degrees Celsius. Superheated steam is very dry steam, and that's what they run through the turbines. And the reason for that, at that high temperatures, if you had a drop of water in there, it would probably break the turbine vanes that make it spin. When we were on the ship, we typically were burning whatever the fuel was. They had a name for it. I can't remember it now. It's called Navy something or another. But when they burned that in a boiler, they produced superheated steam and fired that through the turbines. That's what turned the propellers and moved us through the water. They could not have any liquid water in that because it would destroy those propeller blades because that was going at a very high rate of speed. So it had to be superheated steam. Okay. So that's what happens when you add heat within a given phase. Okay. But if you have, oh, and by the way, well, we'll come back to this in a second. Okay. We lost the graphic that we need to keep, but the second thing that happens is you can have a phase change. Okay? At a constant temperature, by the way. And this is what we saw in lab. Remember that first question you had in lab. Did the temperature change as the ice was melting? And the answer was no. It was right near zero. Some of the thermometers may have read something other than zero, right at zero. And even though the ice was melting, it still was at 0 degrees. And guess what? When you're cooking your food and you're boiling your beans or whatever it is, does it help to turn up the no, the water's going to be at the boiling point, 100 degrees Celsius, 212 degrees Fahrenheit. Turning up the heat just makes it evaporate faster. It does not change the temperature of that water. So once it starts boiling, cut it down just to the level to keep it boiling. You're not going to cook it any faster. Now, if you're grilling, yeah, that's a different story. There's no water involved there, okay? But if you're boiling something in water, it's not going to make any difference whether you have it. Now, also what we noticed in lab, what did your mom or your grandma or whoever did in the past when they were canning beans, say, or something like that? What did they usually use to?
The jar they put the package to seal it, you mean?
Okay, yeah, to make it help it seal. My mom used to use a pressure cooker. Have you heard of that? What is the advantage of a pressure cooker?
It's something to the jar.
Oh, okay, what it does is the same thing we talked about in lab. It increases the pressure, and as you increase the pressure, now the boiling point also goes up. So under pressure, and that's why the best thing you can do when you're boiling your beans or whatever is put a lid on it once it starts boiling and cut down the heat. That will keep more heat inside, but also add a little bit more pressure, so they will cook a little bit faster with the lid on than with the lid off. My wife doesn't like to put lids on things, but yeah. Okay, so you have a phase change. That's related to changes in the internal potential energy, not the kinetic energy. Kinetic energy changes temperature. Potential energy changes phase. So when it goes from an ice to a liquid, or from a liquid to a gas, that's a phase change. That happens at the same temperature. That's why we call it the freezing point, or the melting point, or the boiling point, or evaporation point. In that case, we're dealing with a different kind of heat, not specific heat. Specific heat depends on temperature change. You're dealing with what they call latent heat. Now, that word latent really comes from the same root as the word hidden. It's hidden heat. You don't feel a temperature change, but there's more heat involved with it. And that's why steam at 100 degrees Celsius or 212 degrees Fahrenheit will burn you far worse than water. They both burn you. They both hurt. But steam will actually do more damage because it doesn't just have the specific heat, it has latent, hidden heat in it at the same temperature. Now let's see. Let's go back to the previous graphic, even though it has the other thing here. As you warm that ice to get it up to the melting point, it just gets ice at a warmer temperature. It doesn't melt until you reach that freezing point or melting point, then it starts changing phase. Once that happens, the temperature stays constant, 0 degrees, 32 degrees Fahrenheit, until all the ice melts. Then once the ice melts and it's all liquid, now it looks like there's still some ice in there to me, maybe not. Maybe that's just a glass. Okay? But once the ice is melted and it's liquid, you add heat, you change temperature. And you go from 0 degrees up to the boiling point. Once you reach the boiling point, the temperature stops there, even though you add more heat or you continue boiling. Now you're changing phase from liquid to gas, and the temperature stays constant until all of that liquid is gone, and at that point, it starts heating up. Like that pan you left on the stove, it doesn't damage the pan any until all that water is gone. Then the pan increases in temperature, and you start warming the pan. That happened only after all the water was gone. Okay? And then you're adding more heat and you're changing temperature again. So here is the graphic that shows that. Okay? When you're anywhere, and this is degrees Celsius, so this is Celsius scale. If you have ice down here at minus 20 degrees Celsius, that's probably a little colder than your freezer makes it, but you could still have it down there at minus 20. You add heat to it, is it going to melt? Not until it warms up first and gets to 0 degrees, then it will melt. Now this actually happened to me when I did graduate work at University of Nebraska-Lincoln, which to me is really cold. Though there was a guy I worked with who came from Minnesota. He said he moved south to Lincoln to warm up. I thought, no, that's plenty cold for me. I'm not going any further north if I can help it. Okay. So anyway, when I was there, we were coming home. A guy was giving me a ride home for Christmas. And when we left Lincoln, it was so cold. It had snowed, and it was so terribly cold. Even though there was snow on the road, none of it was sticking to the road. It was so cold, it was blowing like crazy. When we got down about Kansas City, we reached the point where some of that snow was beginning to melt, and we were right, and then it was getting really slick. But I did not realize you could be so cold that the snow doesn't stick. Okay, and you couldn't make a snowball with it; it just fell apart. Because really, what you do with a snowball, you add pressure to it. You melt a little bit. When you release the pressure, then it refreezes, and that gives you a snowball. You couldn't do that. You could not add enough pressure to it to melt any of it. So it warmed from state ice from -20 up to 0. Once you reach 0, some of that starts melting. And it stays at 0 degrees until every bit of that ice melts. Here you had only ice. Here you have ice and water. So in your cup there, do you have any ice in it still? Yeah, so you're right around 0 degrees. In fact, Celsius, 32 Fahrenheit. In fact, since I'm guessing that may have a little bit of sugar in it, maybe, you're probably a little below that. Because sugar actually depresses the freezing point, or salt, or anything. So you're right there. As long as you have liquid and solid present at the same time, you're right close to 32 degrees, melting point. But once all that ice melts, now it starts heat. You keep adding heat, and you start warming that liquid. And it increases temperature, until you reach 100 degrees Celsius, the boiling point. At that temperature, you can add more heat. It just boils faster, but it still doesn't change temperature. It maintains that temperature as long as there's water and water vapor present together. It maintains 100 degrees. Until it all becomes water vapor, then you keep adding, and then it gets hot. Very, very hot. They don't show how hot, but the superheated steam they use in boilers and things like this are usually, I'm thinking, around 500 degrees or so. Okay, so very, very hot. That steam will do some serious burning. Now that's what happens if you're adding heat. But guess what? You could be taking heat away. And when you take heat away, that water vapor now condensed, it cools until it gets to the condensation point, which is the same as the boiling point, and at that point, now it begins to change from a vapor to a gas. Gas to a liquid. And during that time, it doesn't change temperature again. This is a phase change. When it all becomes liquid, then the liquid starts dropping in temperature as you take heat away, until you reach the freezing point. Melting point, freezing point, same thing, just which way you're heading. And at that point, it all stays at 0 degrees until it all freezes. And once it's frozen, then the ice starts dropping in temperature again. So the constant heat input, constant heat loss. Just draw that at the top. They drew this and labeled it for the other. Now, anytime you have an increase in temperature, then you're dealing with specific heat. Q is equal to C m delta T. Change of temperature. But when you're having a phase change, solid to liquid, liquid to solid, liquid to gas, gas to liquid, then you have a constant temperature. Specific heat formula won't work because you don't have a change of temperature. That's when you have latent heat. And unfortunately, they didn't put it on the graphic, those formulas. So let me put it there for you. Or if they have it somewhere else, this is where you should put it. So the latent heat, that formula, I'm going to need to get a light color. We have yellow, orange, light green, maybe even light blue or light red. What you want?
Let's do like
Light green. Let's try that and see if it'll show up. Okay? The formula for latent heat is on page 100, and there's actually two of them. There's the latent heat of melting, also called freezing, also called fusion. That's the one down here when you're going between a solid and a liquid. There's another latent heat up there at the phase change of liquid to gas or gas to liquid, latent heat of vaporization or latent heat of condensation. Okay? We'll use the lower one there. Remember, heat is what symbol? We used it, Q. Yeah, that shows up okay. Q is equal to, remember we had mass, still have mass. Whereas we had specific heat before, we have what they call latent heat. Now, since we're talking about the one down here, that's going to be latent heat of melting or freezing. The generic term is fusion, the latent heat of fusion. That's it. There's no delta T. Now, so that's Q for fusion or freezing or melting. The Q for vaporization or condensation, most of the time we use vaporization. That formula is M times LV, latent heat of vaporization. Those are equations 4.5 and 4.6 in your text. Okay? Now, I think they're going to show the graphic in a minute. If they don't, I'll give them to you and tell you what those values are. But that's how much heat, and by the way, the units for that latent heat, remember for specific heat, whose symbol was C, the units for that was calories or kilocalories per gram degree Celsius. Well, we still have the latent heat of fusion or vaporization is going to be in calories or kilocalories per gram. There is no degree Celsius because there's no change of temperature. So this is the unit for this. Now you can have kilocalories per kilogram, or you could have joules or kilojoules. You know, you can have different units for heat. That would be what that is. Multiplied by the mass in grams, and the grams go out. Mass in kilograms go out. Okay. So this one down here is the boiling or vaporization. Okay. Now the numbers are different, but the units are the same. All right, let's go to, okay, here's the phase changes. Latent heat is what is gained or lost when you go from solid to a liquid. That's called melting, but the latent heat is usually called the latent heat of fusion. When you go from liquid to gas, we call that the latent heat of vaporization. And you also have latent heat of sublimation, which is going from a solid to a gas. Can anyone think of any material that goes straight from a solid to a gas? Dry ice, very good. Did you see it in the book, or did you know that already? Okay. Have y'all been to concerts where they had, it looks like clouds all over the place there? Okay, yeah, a long time ago. I haven't been either. Okay. What that is from, they have dry ice down there, and that's not dry ice that you see, evaporating. What it is carbon dioxide is coming. Dry ice, by the way, is solid carbon dioxide, and it's evaporating, going straight from a solid to a gas, and that's what you're seeing. But it's such a cold temperature that the moisture in the room then starts condensing. So what you're seeing is really a cloud, water vapor that's doing, but it's happening because that's happening at such a low temperature. Now, when the temperature is increasing, when you're going from a solid to a liquid, we call the temperature at which that happens the melting point. Solid to liquid, you're melting the liquid. When you're going from liquid to gas, we call it the boiling point. Okay? And when you go from a solid to a gas, We call it the sublimation point. We don't change the name. Okay? If the temperature is decreasing though, and you're going from a gas to a solid, that's the sublimation point again. If it's going from a gas to a liquid, we call it the condensation point, or a liquid to a solid, you would call it the freezing point. The points are the same for any given material, like water to ice, or ice to water. Melting point, freezing point, same temperature. Okay, 0 degrees Fahrenheit, 32 Celsius. 0 degrees Celsius, 32 Fahrenheit. These two are the same for water, or for any substance. I just know what it is for water. 100 degrees Celsius, 100 degrees Celsius. 212 Fahrenheit, 212 Fahrenheit. I don't know what it is for water sublimation. There is a temperature that happens, but it's outside the normal range. Is in the normal range for carbon dioxide. Okay. So those are your terms and your temperatures. They don't give them to you, but let's see. No, they don't. I thought they were going to give, let's just see. No. Let's go back and let's fill in the blanks here. I thought they were going to give it. It's in the text. That's why, please read the text. You can't get everything off the PowerPoints. They just leave some stuff out. There is a table in the book. And before I turn the page to get to it, here's passive solar design. This is a little bit of what I was talking about, I believe it was last time. Things that you can do to minimize extreme temperatures, okay? First, you can just let light in. That will warm you up in the wintertime, but it'll also warm you up in the summertime. So we put blinds on the window to keep that from warming you up too much in the summertime. And that's where I told my wife, drive her crazy going around, opening blinds, closing blinds, trying to adjust for temperature. They also show a Trombe wall here. Now, most people don't like that because they have the big picture window so they can see out, Well, if you put a Trombe wall, you block most of the window. But that is a way to absorb some of that heat and dissipate it, okay? It can warm you in the wintertime or get it away from you and cool you a little bit in the summertime. Or you can put a buffer zone out there, okay, that traps the heat, and if you want the heat coming in, open those windows for the convection to bring it in. If you want to keep the heat out there, close the windows, and you have that. Now that's a big example of what they do most days. These old windows here, I guarantee you, single pane. More modern houses, most of them are going to have at least double pane windows. There are some that will actually be triple pane. Those are more expensive, okay? But what they do there, what you're trying to do, is create a dead air space. Dead air is a good insulator, not a good conductor. Glass is a better conductor than dead air, so you have the dead air space. Best if it's actually a vacuum, okay? But most of the time they won't maintain a vacuum for that long. Anyway, really worth the read there. Passive solar design. All right, but table 4.4 and the figure there, 420, is a lot like the figure you see on this one, but this figure that we see here is 418. 420. Sorry. Y'all awake yet? All right. What they do here is give the formulas. When you're warming ice, is green okay here, or would you rather have it a little darker? Darker? Let's go to a dark green then. That'll show up a little better. The formula you use when you're changing temperature is Q is equal to MC delta T, where C is specific heat. When you're having a phase change, then you use Q is equal to MLF, because that's latent heat of fusion. When you're changing temperature again here, it's Q is equal to mc delta T. That's a pretty ugly delta, isn't it? Now, that looks like the same formula you have here. Does that mean the numbers are the same?
Yes.
No. C for ice is like 0.5. C for water is 1.00. Go back to your specific heat table earlier in the chapter and you'll see that. The boiling point or condensation point, you go back to a phase change. Q is equal to ML, but this L is LV, not LF. LF is a latent heat of fusion. This is latent heat of vaporization or condensation. Then when you're warming steam, getting it to higher and higher temperatures, you go back to Q is equal to mc delta T. But here your C is the latent heat the specific heat for steam, not for liquid water and not for solid water. Ice is steam. That's 0.48. So it's a little bit different from ice, but very different from water. So you got two basic formulas here, but for the different materials, you have different C's. This is the C for ice, the C for water, C for steam. Here you have latent heat for fusion, latent heat for vaporization. The forms are the same, but you put in different numbers. Okay, we'll do an example with that a little bit later. Now, that's the table that you have at the top of 102. I filled in the formulas for you on this table because I don't show this table again. But let's look at table 4.4. I was calling that a table. It's a figure. This is table 4.4. Some physical constants for water and ice. For water, the specific heat, the one that you have here, this one is, let's see if, yeah, it'll right here. That would be 1.00 calories per gram degrees Celsius. Now, if you wanted to make it kilocalories per kilogram degrees Celsius, still 1.0. For ice, down here, this C is 0.5. Same units, and do they put any? Yeah, they put two more decimals on it, which I'm not sure it's that precise, but it's calories per gram degrees Celsius. You still have the same units because it's specific heat. Over here, this one for steam is 0.48, isn't it? Yeah. And it's still calories per gram degrees Celsius, or kilocalories per kilogram degrees Celsius. Now, the latent heat of fusion, whether it's melting or freezing, whichever way it's going, this latent heat for fusion, I'm going to write it over here. That's here and here. And what number would that be? They give it here is 80.0 calories per gram, or kilocalories per kilogram, either one. The latent heat of vaporization that you have here, that one is 540.0 calories per gram. So where's most of the heat being absorbed or dealt with? And then they have the one more down here that we've used several times before, and they actually put it strangely. I don't really care for this. Okay, I like to either have calories in joules or kilocalorie in kilojoules. Comes out the same, but 1 calorie is 4.184 joules, or 1 kilocalorie is 4.184 kilojoules. You just multiplied everything by 1,000 and it stayed the same. What they did is take the kilocalorie here and move the decimal 3 places there and make it 4,184 joules. Why, I'm not sure. I'll just leave it like that. But anyway, those are the numbers that let you know things are a-changing here. But most of the heat happens with that latent heat of vaporization. Boy, that's absorbing a lot of heat. All right, I think we're ready for example 4.7. So let's see if we can clear the screen here. And see if we can find, that's a good place to put it. In fact, okay. How much energy, so what are we looking for? And what symbol is that? Q, energy or heat, same thing. How much energy does a refrigerator remove from 100 grams of water? What's that a measure of? What does that measure? What does grams measure? Anybody? What does grams measure? Mass. That's your mass. This is mass of the water. Okay? So how much energy does a refrigerator remove from 100 grams of water at 20 degrees, 20.0 degrees Celsius? Now that, in this case, is going to be our, not delta yet, that's going to be T initial, temperature initially. To make ice, so you're going to make ice, this is water, you're going to make ice, and that ice is going to be at negative 10 degrees Celsius. 10.0 degrees Celsius. Okay? That's going to be your T final. But, do you do that directly? Yeah, do you go straight from 20 degree water to minus 10 degree ice? No, you don't. What's the first thing you're going to do to that 20 degree water? That refrigerator is removing heat. That's what we're looking for, Q. Would it be better if I went something lighter than this, like light green? Because that is a little hard to see. Let me change to light green. Okay, what's the first thing that's going to happen to that water at 20 degrees Celsius? Put it in the freezer, what's the first thing that's going to happen? It doesn't start freezing at 20 degrees.
It's gonna absorb the cool.
Okay. Actually, we often say it loses heat. Okay, loses heat to its surrounding, so it's going to chill the water. Okay, how far will it chill the water? To 0 degrees Celsius, exactly. So let's do it first. So what we're first going to have is the Q for cooling. Okay, and what formula do you use for Q for cooling when you're changing temperature? Liquid water, cooling it. M, C, delta T. Okay, now we already know our mass. That's going to stay the mass. That's going to be 100.0 grams. What C do we use for liquid water? Little c. Specific heat of water. It was on the last slide. It's in that table on page 102 or thereabouts. What is your specific heat, little c, for water? 1.00 units, calories per gram degree Celsius. And what's your delta T here? Yeah, it's 20 degrees because you go from 20 to 0. So your delta T is 20 degrees. Not to minus 10. You're chilling the water only to 0. So that's your delta T. All right, so now you see your grams will cancel out. Your degrees Celsius will cancel out. You just multiply across there, and what do you get? 1, that I can do that one, times 20 would be 2,000, and what unit do you have left? Calories. Or you could call it, if you wanted a smaller number but a bigger unit, that would be the same as Bigger unit would be kilocalories. What would be the smaller number then? 2.0 kilocalories or whatever. Okay. So that's the first thing you do. Chill the water. There's the formula used. Then what do you have to do?
Now you have to
No, not warming. Your refrigerator is? Your freezer is? Freezing it!
freeze.
Okay, what formula you use for freezing that water?
Okay, for freezing the water,
What's that? M times LF, exactly. Your mass is still to 100. You haven't lost any. It's still 100.0 grams. And what's the latent heat for fusion for water? 80.0 calories per gram. And what does those multiply to be?
say 100 times 80.
Yep, 8,000 calories. Or if you wanted to do a smaller number, bigger unit, that would be 8.0 kilocalories. Okay. Now, I want to point something out to you. Same 100 grams of water you have there. Same 100 grams, okay? Did you finish? Okay. Same 100 degrees. Do you think it took more energy to cool that water at 20 degrees or just to freeze the water at the same temperature?
I believe it's going
Okay? Does it take more energy to cool the water at 20 degrees or to freeze the water at the same temperature? The numbers are right there. It takes more energy to freeze the water than it does to cool the water. 20 degrees, 100 degrees, let's see, 100 degrees, well, you would have been a little bit more, okay? But that's a huge change in temperature. For a pretty decent change in temperature, that's room temperature to freezing. It only takes 2 kilocalories of heat, 2,000 calories of heat. But to freeze that same amount of water without changing temperature at all is 8,000 calories to remove. Okay, well, you got one more step to do. What is that? Because they said to get ice at -10, we've only got ice at 0 degrees. So what you got to do? You got to cool the ice. Cool the ice. So you go back to cooling the ice. This was cooling the water, and this is cooling the ice. Okay? What's your formula again? MC delta T. Exactly the same formula, but what changes? Does the mass change? No, that stays 100 grams. But what does change? Okay, you do have a change of delta T, but what else changes? What's the next letter there? C. That means yes. No, never mind. What's that?
Steam.
No, it's not steam. Ice.
Ice.
Specific heat for ice is 0.500 calories per gram degrees Celsius. Okay? And then what is your change of temperature then? What it? You throw it at her, huh?
No.
Okay. All right.
Now you want to know the number 4. We had 0.5 for C. Now temperature.
What is your temperature change? 10 degrees, because you were at 0. That's where you froze it. It went down to 10, so that's another 10.0 degrees Celsius. And what does that multiply to be?
Okay, so you say 100.
500, no, times 10.
Times 10.
Wait, no, wait, hey. I think you're right. Yeah. 0.5 times 100 would be 50 times 10 is 500. You're right. 500 calories. Okay? Now, you could change that to how many kilocalories? 0.5. I just don't have room, so I'm not going to do it. Okay. But yeah, you see, that simple statement actually had 3 steps in it. You have to first cool the water, freeze the water, and then cool the ice. Not bad. Think, keep it with it. Okay. That's what we got. So you add, let's see, what was the question? How much energy does the refrigerator have to remove? Well, you have to add those together. That would be 2,000 calories and 8,000. That's 10,000 calories plus another 500 is 10,500 calories. So we make that, if you do it in kilocalories, that would be 10.5. And what they do, strangely, is make it times 10 to the third calories. Why not use your prefix to do that? 10.5 kilocalories. That's what kilocalories is. Kilo means 1,000. 10 to the third is 1,000.
Didn't you say before that they use
What's that?
big calories instead of the kilocalories?
Okay. The only time we really use the big C calories is when we're talking about foods. Okay.
I was just wondering.
Yeah, but it is the same. A kilocalorie is a big C calorie. So,
I'd rather do it that way to keep from being confused.
yeah.
Calorie stuff anyway.
Right.
I'm just asking.
Yeah. So, that's, and a big C calorie is a kilocalorie, or 10 to the third calorie. But we usually do that when we talk about heat content of food. In other words, when you metabolize the food, how much energy are you burning? Or how much energy are you taking in, how much calories are you taking in you're not metabolizing? So they're just collecting in there. Okay. Now I think we're ready for the next slide, which is evaporation and condensation. Okay? This begins on the very bottom of 102 and moves from there. Now, don't know if you recall, but we said when we're talking about temperature, the average kinetic energy of the molecules. The reason we put that in there, if you have a material, any kind of material, some molecules are going to be moving fast, some are going to be moving slow, because it's the average you're dealing with. Okay? Same thing is happening, especially in liquids and gases. You have a variety of temperatures of individual molecules. So individual molecules can change phase at any time if this one molecule happens to get so energetic because it bounced into another one and got enough kinetic energy to leave, to evaporate from water to a gas. You know that. If you leave a pan out in the room long enough, that water will evaporate away. Unless the room is 100% humidity and stays at 100%. But boy, in the wintertime, in fact, when I was up in Nebraska, the heat was on big time in the wintertime, and the air got so dry inside that I got headaches and things, and I think either a doctor or somebody said, put a pan of water on the stove. Yeah. And so what I started doing, what's that? It basically you're humidified.
My grandmother did that when I was little.
Yeah.
I didn't find it out until in my own house.
Yeah, that's exactly what it is. In the wintertime, when you're heating, you tend to be drying out the air because the air outside can't hold much moisture. You warm it up when it gets inside, it holds even less, so you're dropping the humidity. And frankly, I grew up in the South where it's very humid. My sinuses and everything else is used to a lot of moisture. And when they didn't have them humid, they felt bad. So those molecules can change phase at any time. So what we did, we had it was a gas range in the kitchen, the first place I lived when I was there in Nebraska. I moved in with a guy when his sister moved out. He was used to it. He was from Omaha, so it didn't bother him any. But I said, and the old stove had a pilot light in it. A lot of the new stoves don't have that. But there was a pilot light, and you had to watch it. If you put something down in that part of the stove, it's going to get hot, okay? So that's what I put my pan of water over the pilot light. So whether we were using the stove or not, it was still evaporating. And the other thing I did, which probably most people would have said was crazy, maybe it was, but when we were drying clothes, because when I moved in, I had a washer dryer. He hadn't had one, but it had a utility room out by the stairwell that had hookups for it, so we did, but it wasn't heated there, so most of the time we kept that door closed in the wintertime especially. So when I was drying clothes, I opened that door and blew the vent. I unhooked it from the wall and blew it into the house, closed the door as much as I could, and added a lot of heat, moisture to the room. Made me feel good. And then when the dryer shut off, closed that door again, back again. So most of the wintertime, I never even hooked it to the wall. I blew it into the house, and it would steam up the windows sometime, but boy, it felt good to me. All right, so evaporation. The energy required to overcome the phase cohesion, we saw that it happens at 100 degrees Celsius, but the individual molecule may have enough energy to take off anytime, okay? The higher energy molecules near the surface can then escape. And here's the picture they're referring to. All right, here's a container of water. Now this water has some molecules with 5, and they don't say what units. Let's just call them kilocalories, okay? And these other molecules have 10, others have 15, and a few others have 25. Well, if they had really drawn this properly, the 5s would have been near the bottom because they're moving more slowly and they're denser. The 10s, they're all mixed up. And the 15, but the 25s they got right. They're near the surface because they've risen there. Well, if that's enough energy to escape, then those two are going to take off. Well, what do you measure your temperature by? Average kinetic energy of the molecules. So if you added all these together, 25 and 25 is 50, 60, 70, 80, 90, 100, 105, 115, 115. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 molecules. 115 divided by 10 was an average kinetic energy of 11.5, which isn't nearly hot enough to boil, but these molecules happen to have enough energy to leave. So your average kinetic energy was that. But then when these two molecules leave, what does that leave you with? Okay, you have a lot more than 10 molecules, by the way. This is the average. You've lost those two. Now you're down to 8 molecules. And what are they? 10, 20, 30, 40, 50, 65 divided by 8. That's down to 8.1. So your average kinetic energy here is much higher than it is here. That temperature is that water is warmer than this temperature. Okay? Now I don't know if y'all have ever done this. I haven't myself, but I've seen pictures of it. Especially out in the Rockies, okay, where the humidity is very low and the hikers are hiking, they carry their water in, this sounds absurd, but canvas water holders, okay? And a little bit of water that doesn't leak through, but is on the surface and it evaporates, chilling the water, so when they drink the water, it's cooler than the outside temperature. If you had it in a metal container with no ice in it, it's going to rapidly become right what's outside. Then you're drinking tepid water and you think, but when you drink it in something that's allowed some evaporation, that drops the average kinetic energy, which drops the temperature. That's called radiative cooling. That's kind of what your radiator does. It allows the heat to be taken away. Of course, that's through metal. It's not the same as this, but that's indeed what's happening. Okay, so the higher energy molecules near the surface escape, dropping the average kinetic energy, meaning the temperature of that. Condensation, the molecules near the surface lose kinetic energy to liquid molecules and they merge. Now that happens in a very humid environment, say in the summertime, when you have a glass of ice water. Not in a styrofoam cup, but in a glass or maybe even a metal cup. And what you notice, as soon as you put the ice water in, you get condensation on the outside. Why? Because the water moisture that's in the air at high levels of humidity, as soon as it sees that cold glass, those water molecules come out of the air and condense on the side. Now, we were doing radon research and using as a consultant this guy who had really sharp guy from upstate New York, way up there, Schenectady or somewhere like that. He came down to Orlando, Florida for a meeting, and he could not believe it. He had never been in that humid of an environment. It was in the summertime, that you poured a glass of ice water and immediately the condensation happened. He thought it took minutes for it to happen, because that's what it did up in upper state New York, where there wasn't that much humidity, and they didn't drink that cold ice and things, and stuff. They usually just drink tap water probably. Well, guess what? He was surprised at how fast that condensed. Lacey's here, 10 o'clock scholar, okay? All right, good deal. How are we doing on time, by the way? 4:54. Huh? Yeah, right. 4:55. Okay, we've got 50 minutes till lab time, so I think we can maybe finish the chapter. Okay, looks like we can anyway. What we're moving now is into, I think this is the last major division. Yes, it is. 4.5, and that's thermodynamics. But before we get there, good. Zach is here. Okay. They do have a figure 422 that shows some condensation inside a Listerine bottle. For what's that worth? They have a lady hanging out clothes. Y'all remember when people did that?
I used to do that.
Yes, I used to too.
Yeah.
Yeah. What's going on there? The damp clothes, the water is evaporating into the dry temp. Now, there's a couple of reasons you don't hang out clothes right before it's going to rain. Number one, the air is already very humid, and you're not going to lose a lot of moisture from it. And then the second thing is you hang them out and the rain starts, it's all wet again. So not a good idea. But on those days when it's a real good drying day, that's when you hang out the clothes. Okay? And even in the wintertime, clothes would still dry. Take a little longer, but if it was dry outside, not near 100% humidity, it would work. Now there's a concept applied. Why is it called a pop can? And that's not really the reason, but if you think about it, if you read through this, you'll see that that's exactly what we did in the lab Tuesday. Well, yeah, it was a soda can, if you want to call it that, and it did, if y'all were there, you heard it pop when we did what we did to it. I know, I do too. My wife doesn't want one, but I think I call it a solar-powered clothes dryer. Okay. So, anyway, 4.5 is starting thermodynamics. We've already mentioned this word way back early in the chapter. Thermo means heat, basically. Dynamic or changing heat. So what it is the study of heat and its relationship to mechanical and other forms of energy. That's what thermodynamics is about. Talk with engineers, they just call it thermo. Yeah, made a D in thermo or whatever. Okay. Pretty tough subject. Okay. Not everybody makes these, by the way. Anyway, thermodynamic analysis includes. Here's what you have to do. When you talk about thermodynamics, you're talking about the entire system. So in other words, this is a macroscopic concept. You influenced by the microscopic, but you're looking at the macroscopic, the entire system. Not only the system, what's surrounding the system, everything outside the system that influences it. Okay? So you have to keep both of those in mind. But you are thinking what's going on microscopically, the internal energy, that's the total internal potential and kinetic energy of the object in question. Not so much the external energy, looking at mostly the internal energy. And that would be potential and kinetic energy of the object. Now, we have energy conversions going on. One very common one is friction, okay? For instance, how do you stop your car? Friction, exactly. What does pressing the brake do for you? Pushes the brake drum against the brake pads, or whatever they call the terms now. Is that still what they call them? Sort of, roughly. What do they call them now? What?
They're discs instead of drums.
Discs instead of drums.
Pads on the.
Yeah, the pads on the disc, okay. Instead of drums, okay. I'm old, okay.
No, it's just.
All right.
They still have them.
Yeah, they still do. So anyway, what you're doing, you're pressing those together, the friction, and if you've ever touched one of those after someone recently brought it in, you probably still have a scar, okay? Those things are hot.
Yeah, that's why.
Look up, yeah.
They got to cool off.
They've got to cool off before if someone brings it in, you usually let it sit there a while before you go to change it. Otherwise, you're going to burn something, okay? Friction converts mechanical energy into heat energy, okay? Now, we'll talk about a couple of different applications. First is the heat engine. Basically, that's your internal combustion engine or things like that. Devices that convert heat into mechanical energy. Because what's going on in your car? You're burning the fuel, and when you burn that, you're expanding a gas big time. The expanding of the gas pushes the piston down, turning the crankshaft, and that's what goes from heat, the burning of the fuel, and the mechanical energy, the moving of the car. Whereas braking the car takes the mechanical energy of the car and converts it by friction back into heat again. Can you use this heat again? Generally not.
Jay Leonard has a car that runs, it's an old car, it runs off steam from the water.
Okay, who has that?
Jay Leonard.
Jay Leno, the former, yeah. Okay. Actually, I can't remember which one it is. I think it's Toyota hybrids, and maybe all the hybrids.
Yeah, they break as soon as you.
Yes, they use.
And it used the brake power.
Okay. Rather than converting to heat, though they're probably a little bit, they convert it back to electrical energy, recharging the batteries so they can use it again. That's a smart move. Okay. Don't have the wasted heat. They have reusable electrical energy. It's called regenerative braking, okay? Because you're regenerating electricity with the brake. Because in order to do that, and here's something I've always thought ought to happen, and I think some places do it now. All these exercise places, you see them side of the road, the Gold's Gym, all like this. A lot of the things in there, they have, these people on the mechanical bike, stationary bikes. Seems like to me, rather than that being a heat producer, why aren't you generating electricity with that and cooling the room rather than heating it up? Yeah, it's not going to be much, but it seemed like to me every little bit would help. Okay.
Yeah, if all the machines.
Yeah, if you had all machines feeding into, why not?
Wow.
Okay, that's my weird way of thinking. Okay, other applications. You have heat pumps, which go another way. You take mechanical energy by compressing, and you create heat. Okay, compressing the gas. Refrigerators start that way, but then let the refrigerant expand rapidly, and that cools. Okay, organisms. Okay, we are organisms. Microorganisms are organisms. Basically, what they take is carbohydrates or fats, hydrocarbons, and oxidize them. That's why we have temperatures, okay, because we are constantly burning, but then we're regulated. So organisms are taking stored chemical energy and creating motion, mechanical energy, also some heat. Hurricanes. Good, bad, or indifferent? Do you think hurricanes are good, they're bad, or indifferent?
The generator on it, they gotta be a little good.
Okay, they certainly are. They do a lot of damage, so most people think hurricanes are bad news. But if we didn't have, what's that?
If it wasn't a bad one, I guess it would be.
Right. But what happens is that's the way to get the heat from the equator up into the temperate and maybe even to the tropical areas to dissipate that heat. Otherwise, the equatorial areas would get way too hot and upstream would get way too cold. So that's how the Earth manages its heat flow. Thermodynamics, moving heat around. Stars. Okay, stars basically are, they call it burning. It's not really burning. They're nuclear reactions going on there that are producing enormous amounts of energy. Okay? Black holes, on the other hand, we don't know exactly what they're doing. They're awfully hard to figure out. They seem to be sucking in things like crazy, especially matter. Okay? But I think even energy, even light energy can't leave it sucked in. So whatever's happening there, going the other way. Virtually any system with energy inputs and outputs are involved with thermodynamics. Okay. There are three basic laws of thermodynamics. Really, some people say four. William Thomson, Lord Kelvin, that the temperature scale was named from, was primarily the main guy who put together these three laws. But afterwards, like generations afterwards, someone said, you know, we really need another law, but it really precedes the first law, and they named it the zeroth law. And that law is actually the law of thermometry, basically. If one object's touching another object, they come to thermal equilibrium, they're at the same temperature. Yeah, so basically something like that. We'll not go into that, but you know basically what's happening there. First law of thermodynamics is basically an expression of the conservation of energy. Basically it is. The components are your internal energy, the heat that's given off or absorbed, either way, it can be plus or minus, work that's being done on the system or by the system. And again, that can be positive or negative. And that creates, and actually internal energy, I like to put a delta there, change of internal energy. So stated in terms of changes in internal energy, that's what I just said, and it can be because of adding or losing heat, doing work or having the work done on it. Okay? Applications, heat engines are one of the primary or primary ones, just like your car. So here's an example of this, kinda. Okay? If you start with a cylinder of air and you have a tight fitting piston around that, so none of the air is escaping, but then you put a weight on top of that, that's going to compress the gas. Okay? Basically, this weight has done work on the gas, compressing it. But then if you turn around and add heat to the container, now the gas molecules move at a faster rate so they pick up energy, internal energy. You're heating them, and that does work on the weight. So as you see, initially the weight did work on the gas, but then by adding heat, you can do work on the weight. Okay? All of it is change of internal energy. Okay? Here, you did work on the gas. You probably increased the gas's internal energy a little bit, but most you did because you did work on it. Okay? But then when you added heat to it, then you added to the heat of the gas and did work on the weight. So everything is measured by that. Let's see if they show the formula. I can't remember if they do or not. Here's another way to look at that. You have I really don't like the way they have this stuff, but I guess it's okay. Your high temperature region, and we're talking about heat engines, so we'll talk about an automobile engine, internal combustion engine. Have a high temperature region, you just exploded the fuel in the piston. That's a high temperature region. It's doing work on the piston, which then moves the car. So you have some work going out. But that hot gas that's left over, you have to do something with it. Of course, it's lost some of its heat because that heat has become work, but you still have hot gas, and that goes out the tailpipe. And that's why our internal, and this whole thing is a heat engine, our whole automotive industry, sorry about this, guys, very inefficient, okay? Maybe 15% efficient. Of the energy you put in, an awful lot of it goes out the tailpipe. A lot of it goes out in the radiator. Yeah, a lot of it, some of it moves the car, but even to stop the car, it goes heat in the brakes, okay? So really, it's a very inefficient system. But it works, and it does real good for us, okay? Don't have anything better yet, okay? Now, I don't know exactly what should be there. Oh, I know what should be there. Let me put it there. Let's express this in an equation. This is your equation 4.7 on page 105 or somewhere thereabouts. Now, I really don't like their way of naming it, but JQ, okay, that's heat, okay? Why don't they just call it heat, okay? They call it JQ. It's the joule equivalent of heat. That's what it is. So this is the heat part.
That always be 4.184.
Say again?
That number always be 4.184.
Okay, that's the thing that converts it, yeah, from calories to joules. And everything else is in joules. Minus the work. So in other words, you've added heat, but you've done some work with it. So, okay, let's go back to this, okay? Here is, let me start over on this. Okay. The JQ, goodness gracious. Okay. Why is this not? Okay. Now, the JQ is basically the joule equivalent of heat. That's when you had your explosion in the piston. That's the heat that you added. Minus the work that went out of the system. That's your work down here. And that's usually measured in joules, okay? So that's why we do joule equivalent of heat. Heat is in calories and joule equivalent is 4.184. That gets it into joules. Minus the work. That then is creates the change of your internal energy. Now I like to say IE. They like to use U2 minus U1. I would just as soon call that delta U or delta IE, internal energy. That makes more sense to me. But they use that. So that's what we're talking about, stated in terms of change of internal energy, and that's where the internal energy is on the right. The heat is JQ and the work is W. What that's saying to you is, if you're adding heat, you're either going to do work or you're going to increase internal energy. One or the other. It's got to lose it as work or add it as internal energy. Okay? This is your internal energy that gets wasted somewhere. Change that. The work is what goes this way. Now, if you add heat and you use all that as work, then you don't change your internal energy in. Okay? Now, if you did work on the system, then you're adding work to it. That's either going to increase the heat or it's going to increase your internal energy. Okay? So all that formula works out pretty well. Okay. Now, what I just said before, and they just mention it here, it's another equation for you, but the slide set doesn't address it at all. If you use all your input, if you don't change your internal energy any, In other words, all your input goes to work. Then that work is, if this is 0, if this part over here is 0, then you can rearrange what you have left, before that, and say your work, move it to the other side, is equal to Q high minus Q low. So in other words, if the change of internal energy here from the high temperature to the low temperature regions, that's your calorie decline. If all of that goes to work and doesn't increase internal energy, then you get 100% efficiency. You never get that, so that would be that's the case there. So that's your okay. I've got to add the joule equivalent. Yeah, let me put it in front, because this is usually in calorie, that's usually in joules. Okay, so that's where the J comes from, joule equivalent. Okay, so there's your first law of thermodynamics. The second law of thermodynamics, you have 3 different equivalent statements here. Okay, first law is basically conservation of energy. The second law is 3 equivalent statements. You can separate it this way, express it this way. No process can solely convert a quantity of heat into work. Like we saw in that last equation, that really doesn't happen. You always have some loss, heat loss. Never get away from it. Friction's always heat loss. Unused heat is heat loss, okay? You never use all the heat that you produce. That's one statement. Here's another statement. Same thing. Heat never flows spontaneously from a cold object to a hot object. Heat never flows spontaneously from a cold object to a hot object. Of course not. It always flows in the opposite direction, from hot to cold. But your refrigeration or your air conditioning system, okay, it's making that happen. So it's not spontaneous. You have to force it to happen. So there's another way to express this. The third way is sort of a little bit more generic than this one's for sure. Natural processes tend toward a greater state of disorder, and that's called entropy. Okay? That's the most general statement of the second law. And there's a few really dumb examples. The book will mention some. I'll give you the one that I think is the most. Okay. Let's say you went out and bought you a brand new deck of cards. Okay? You open the package and bring them out and spread them out and look at them. They start with the ace of spades to the deuce of spades, the ace of hearts to the deuce of hearts, the ace of diamonds to the deuce of diamonds, the ace of clubs to the deuce of clubs. They're all put in that way. Okay? So you fold them back up into the deck and say, okay, I'm going to throw them up into the air. And I've got a sheet down here. I'm going to catch every one of them. Okay? Are they going to come down in the same order you just threw them up? No way. In fact, they're not even going to be facing the same direction. Okay? Then the question is, if I had 4 people at each corner of the sheet and threw them up carefully over and over again, will I ever get them back into the same order they were before? Never, ever, ever. Everything, natural processes tend toward a greater state of disorder, never toward a greater state of order. Always to disorder. Look at our living room, okay? Look at the house. It never straightens itself. It always seems to get in a greater state of disorder, okay? My sock drawer. I mean, nothing, it never gets into a better state. It gets into a worse state of disorder, okay? That's entropy. Greater state of disorder. Entropy. Entropy is always, I can't remember, disorder is increasing. I think that's how they refer to it. And guess what? That's true in the universe as well. Nothing on its own, natural process, ever goes to greater disorder. Greater order. It goes to greater disorder. All right. 2 reference scales. We can look at the object's external energy. Now that's the energy of the global coherent motion. I throw a baseball to you. That's giving kinetic energy to the ball. External. Okay? Associated with work. I did work on the ball to increase its kinetic energy when I threw it. Okay? But you can also look at the object's internal energy. The energy of the microscopic, chaotic, incoherent motion that goes on within any object. That's associated with heat. Okay? So the work basically is the coherent motion. The incoherent motion, microscopic, is the heat. You usually can't retrieve that. You can usually retrieve that in most cases. Okay? So let's look at that first thing. Again, it's a lot like the conservation of energy. Your input energy, you would hope, would be the output energy. Okay? If it were, the efficiency of the heat engine would be 100%, or 1. The work done out per unit work in, that would be, if that was 100%, that would be 100% efficient. Energy output equal energy input. The second law says that efficiency can never equal 1. No matter how good a system you have, you're always going to have some loss. Or, other way of saying it, the energy is always degraded, generally to some irretrievable form of heat. Okay. Now, one of the most, I think, efficient things that you have are your hydraulic jacks. Okay? Because with a hydraulic jack, there's very little energy loss. Okay? But there is some. When you compress that fluid, that's what you're doing with the jack, you always have a little bit of heat. And if you had some really sensitive thermocouples in there, you would see it is losing a little bit of heat. Other than that, it's a very efficient system. Okay? Put energy in, you get energy out. But there's always some. Always some. Nothing is ever 100% efficient. Here is the statement from our diagrams before. Your Q high, that's the energy you put into the system, as heat or whatever, is equal to the work that goes out plus the QL. You can never get this QL to be 0. Okay? Ever. Okay? You try to get close, but you never get it to be 0 completely. Okay? Your efficiency within the work you get out divided by the energy you put in. Okay? And because there's always some loss here, this is never 1. E is never 1. Always less than 1. Okay, here's the second way to look at that second statement. Again, we'll look at conservation of energy of a heat pump. The energy arriving, okay, what you're doing with a heat pump, you are putting work into the system. And basically that's your compressor. You're compressing a gas, you're putting work into the system, raising the gas heat to a higher region. Okay? Now, if it's really being used as a heat pump, you try to take this heat and dissipate it into your house or into the heating water or whatever it is you're trying to heat. Okay? So the energy arriving in the high temperature region is energy from the low temperature region plus the work that you needed to move it to get it there. Because what you're doing, you're taking a gas and compressing it. So it had some heat to begin with, okay? Because it had the temperature, it had average kinetic energy. You're doing work increasing that, and that's producing high. So if it's the heat pump side, you try to dissipate that into the house. It's usually pretty good, but you always have some loss, okay? You upgrade the energy in the heat pump is accompanied by a greater degradation in energy elsewhere, okay? And I guarantee you this, in that compressor, there's always going to be some heat loss before you get it into the house, always, okay? There is upgrading of energy by heat pump is accompanied by more loss of energy than you put in, okay? The third statement, real processes are irreversible processes. This is another way of saying it. Throw the deck of cards into the air, it will never come out in the same order you started. The measure of disorder is the entropy. So the second law in those terms, the total entropy of the universe continually increasing. Disorder in the universe. Now sure, there's still stars forming. that weren't there before. That can happen on a certain scale, but the total energy or entropy of the universe, entropy of the universe is increasing, just like our rooms. Okay, they're getting more and more chaotic. Okay, natural processes degrade coherent, useful energy. Available energy in the universe is diminishing because the entropy is increasing. Eventually, they think the universe will die a heat death. Okay? Now, here's sort of the other side of that. The energy can't be created or destroyed, but the entropy is always increasing. Entropy is not the same as energy, but it's related to it. Okay? Now, what they think, and this is into science fiction here, they think, what's happening to that energy that's going into the black holes? Okay? Are we losing it? Or is there an alternative universe somewhere on the other side of that black hole that's now things are reversed? That gets into science fiction. I can't even come close to that. The direction of natural processes is always toward more disorder, greater entropy. Their example is knock over a glass of milk and it spills. Can you do anything to make the milk get back into the glass? Nothing at all. No kind of process. Even taking your Bounty towels and squeezing it back in, you're never going to get it all, okay? Ever, okay? You can't unspill it back into the glass. Everything moves to disorder. Greater entropy. That is the last slide. Before we leave this, though, mistakes and misunderstanding. Can something make its own fuel? Or in other words, is there such a thing as a perpetual motion machine? Never, ever, ever, ever. Have you ever been to the McWayne Center? Okay, isn't that a fascinating place? You know that big device out in front when you first walk in, the balls are just going all over the place. You look at those sometimes, you think, wow, this is a perpetual motion. They just keep moving. But it's not, because if you notice in the middle, there's some little elevator that's hauling those balls up to the top. And then when they release from there, they're like a perpetual motion machine, but at some point they get back, roll together. Something has to add the energy to lift it back up to the top to make all that clanging and banging and everything else happen. Okay? So there's no such thing. We mentioned him last time, Count Rumford, whose name was Benjamin Thompson with a P. William Thompson was without a P, Thompson. William Thompson, British. Benjamin Thompson was an American, but he didn't believe in the breaking away from England. So he was one of the loyalists or the Tories who didn't want the Declaration of Independence or independence from Britain to happen. So he moved back to England, and they made him a count to reward him for coming back. But he was still a very good physicist, scientist, engineer. Worth a read here. If you choose to write on Thompson, Benjamin Thompson, Count Rumford, this is not your source. You can't use this as your source. You have to go outside the book to get your source. This can give you ideas and where to go and how to do it, but it can't be your source. I've read this, so I'll recognize it. If you write on him, I'll recognize if you got it from here. Promise you. Okay. There is one more example, 4.8, at the end of the chapter. So let's see if we can find. Okay, let's write it here. A heat engine operates with 65.0 kilocalories of heat supplied. 65.0 kilocalories of heat supplied. What's the symbol we use for that? Heat. Q. That was our good old Q. Okay? Now, kilocalories heat supplied. Exhaust, 40 kilocalories of heat. Now, by the way, this is supplied, so this is the high energy heat that you put into the system. It exhausts Q sub L, and that was 40 kilocalories of heat. 40.0 kilocalories of heat. That was the output. Heat, not work, but heat. Okay, the low energy side. How much work did the engine do? So we're looking for work. What would that be? Yeah, it's the difference between the two of them. Which is that? Okay, yes, you need to get it. Work is measured in joules. So you can either do the equivalent first, or you can calculate the change of heat and then change that to joules. I find it easier to do that. That would be 25.0 kilocalories times, and what's that joule equivalent? 4.184 what? Okay. The reason they do that, okay, if you're doing joules and kilocalories, you make that 4,000. If you were doing kilojoules, which I was going to do, yeah, but no, we'll do it the way they did. That's equivalent to 1 kilocalorie. Okay? The kilocalories go out, multiply those two together. How much work did you do? I don't have a calculator, so you do it. 25 times 4,184. 104,000, and then they have some other 600. That would be joules. Rounding that to kilojoules, that would be about 105 kilojoules. And that was my question to you. Why use 4,000 here? Why not make it kilojoules there per kilocalorie? Put that as a decimal number. Then multiply 25 times 4.184. What will you get? 105.6. Now, the reason they kept it 3 digits here, they only had 3-digit input here, 3-digit input there. You can't get 4 digits out, so that's why they rounded to 105. Very good. Then there's also a thermodynamics in action, which is well worth a read. Okay? Now, every term I say this, how much time we got? 15 minutes? All right. Okay. All right. Nothing replaces reading the chapter. There is tons more in here than the PowerPoint talked about, than I talked about. Nothing replaces reading the chapter. Read the chapter. But after you do, you can read the summary, and that sort of condenses things. It misses some things, but it condenses most of the high points. Well worth a read there. Then you have your summary of equations. We had a total of 8. And if you were following along and they were doing that, the last one we hit was the equation 4.8. So you have 8 of those. Know them, know how to use them, that type of thing. Key terms, about normal maybe of key terms. They list them alphabetically, but they put the page numbers where they showed up so you can get a better idea of what they are. But the best thing to study or review is applying the concepts. They have 43 questions, maybe a little on the light side, but they give all the answers there. If I were you, though, I would try to answer these myself, recording the answers, marking them down somewhere, checking them afterwards, going back and only reviewing the ones you missed to see, well, why did they get a different answer from me? See if you can work it out. If you can't figure that out, ask me. Bring it to class, and we'll go over. And they may have it wrong in the book, but the odds are there was something a little faulty with your perception. Questions for thought. 17. That's probably a few more than normal. I've seen you before, haven't I? Okay. All right. And then for further analysis, 7. Again, maybe a few more than normal. Then there's who can last longest. That's a interesting little inquiry. For those of you who have the big books, the parallel exercises, the group A have the answers in the back. Work any of those problems, see if you get the answers in the back. If you have the little thin books, still worth working them, If you need to see the answers, I'll be glad to let you take a picture of my answers in the back. Okay. All right. Any questions? What does this mean? Second? I'm sorry.
You're working on what now?
No, I was just telling you things that you would be useful to study for the test.
Okay.
The
well,
parallel exercises on, you see at the end of the chapter.
Okay, applying the concept.
Yeah, after applying the concepts, then parallel exercises. You see those?
Okay.
Those group A exercises in the big books, there are answers in the back. And the little ones there aren't. So if you can get with someone who has a big book, I'll let you look at mine. Okay? If you need that. All right. What this means now is immediately when 5:45 gets here, we're going to the lab and work on the lab. Okay? This is the last lab for chapter 4. Okay? That means on Tuesday when we get back from Thanksgiving, so it's quite a long time, plenty of time for you to study, yes, okay? Then we will start chapter, not 5, but 6. Wave Motions and Sound is a great chapter, but we just don't have time for it, so we're going to start in chapter 6, and in your little book, that is the next chapter, electricity. It should be electricity and magnetism, but it's titled just electricity. We'll start that on Tuesday. We'll probably get far enough to have the first lab. Okay?
Lab for chapter 6.
Lab for chapter 6. But then the last 30 minutes, we'll have the test in chapter 4. Okay? So we have 2 hours of class in chapter 6, a lab from chapter 6, and then 30 minutes, that's 2 hours, and then 30 minutes of test for chapter 4. Okay?
What all do we need in lab? Besides the calculator?
Oh, you mean to take with you to lab? Yeah, definitely your calculator. You might want to take your book just so if you have any formulas to look up, you'll have your book with you. And that's it. And it looks like 2:53 is going to be where we're going to be. How much time do we have left?
It's 5:36.
5:36? Okay, we can get started. Huh? 9 minutes. Let's at least get started on let me get this to do. Okay. Why is this not advancing? Nope, that's not working. Oh, that should have worked. Ah, here we go. All right. The only reason I'm going to chapter 6 now is that we only have 2 hours on Tuesday, and I'm not sure we'll get far enough along for a lab. So I wanted to at least get started on chapter 6.
Make sure I got this.
What's that?
I just want to make sure I'm on point where I know what to study.
Yeah. Chapter 4 is a test,
Okay.
and you can have a formula and equations sheet. Everybody knows that, right? On chapter 4, huh?
Chapter 4, you can have your formula and equations. You can use that study.
And what? And those are the things to study for that. Okay. All right. Especially those formulas and equations, those 8 of them, I definitely have those on that sheet. And anything else you want to put. So let's go to chapter 6. Why isn't it going to chapter 6? Here it goes. This is awfully slow, but it is going, I think. Yeah, it's 5:37. This may not be worth the time it takes to load it, but here we go. Okay, chapter 6 is electricity. I like to think of it as electricity and magnetism. And you'll see the chapter is broken up that way. And even the core concept is that way. Electric and magnetic fields interact and produce forces. They can produce forces. Okay? All right. So we'll be talking both about electricity and magnetism. And maybe a new thing for you is thinking in terms of field rather than actual objects. Okay? All right. Concepts of electricity. people knew about certain things of electricity long before they understood means about it, okay? In fact, when we think of things called static electricity, people knew it happened, but they didn't know what was going on. So here's what we think is going on, and we have a pretty good idea now. It's the electron theory of charge, okay? The ancient mystery was the Amber effect. Now, that's not like Amber Alert. It's the Amber effect. Okay, does anyone know what amber is? Okay, it is a color, sort of a yellowish kind of color. It's what?
Are you talking about the crystallized tree sap?
Exactly, okay? It's fossilized tree sap, exactly, okay? It was an amber color, and what the old mystery was, if you had a piece of this amber and you rubbed it with wool, then you could shock somebody, okay? And no one knew why, but it was a nice little parlor game to go around shocking people with amber, I guess. What fun, okay? They didn't have much to do back then, I guess. But a guy named J.J. Thompson, and we'll run into him again in chapter 8, so the next chapter over, J.J. Thompson identified negatively charged particles that made up atoms and molecules, and these were named electrons. Now, there was nothing that really said they needed to be negative. It was just a convention, okay? And I think they blamed this on our own Benjamin Franklin, okay? He was quite a scientist, but I think he just arbitrarily said, well, let's call the electrons negative and the protons positive, and go from there. And why not, okay? The only thing is that nowadays when we talk about electricity, we'll get to this later in the chapter, you actually have electrons moving from areas of low potential to high potential because they named them negative. So, too bad. But here's what the understanding is. The basic unit of matter is the atom. And that word atom means indivisible. Okay, it can't be divided. But they really can. Not majorly, but they can be. Atoms are made up of electrons, which are extraordinarily tiny. Almost, but not quite massless, okay? And then the electrons float around a nucleus, which is incredibly small, okay? And yet extremely massive, okay? So it has a huge amount of mass in a very tiny space. In fact, you can't get much denser than a nucleus, okay? Because most of the space occupied by an atom is those electrons, and they are flying around way far from each other, comparatively, around this tiny little nucleus that has an enormous amount of mass. The electrons have almost no mass, yet they're taking up all the space. Okay? Incredible. Okay? The nuclei are very dense, very tiny, containing positively charged protons, neutral neutrons, and these are both way more massive. In fact, each one of these, either neutron or proton, is about 10,000 times as massive as one electron. So all the mass is concentrated in that tiny little nucleus, but all the volume is occupied pretty much by those tiny little electrons. Okay? And they go in clouds, and that's what's represented there. So this mass, the nucleus here, the one they've shown here happens to be helium. 2 protons, 2 neutrons. That's a typical helium atom. And actually for helium, you wouldn't have this outer ring, you just have 2 electrons that float around that tiny little nucleus. Okay? They've shown 2 levels. This would be for bigger molecules than what we have for helium. So we'll talk about that again in chapter 8. How are we doing on time? 5:43. Okay, let's see. Probably can't do this in 2 minutes, so we'll pick up next time with electric charge. Okay, so we'll start it right there with electric charge. If I could get my pencil to work. Still can't get it to work. Still can't get it to work. I think my lead is just about gone. Yeah, it worked that time. Okay, we'll pick up there and go. All right, let me go on and give you the labs so I won't have to carry them. I'm lazy. The title of this lab, and this is one I've made up, so it's a lot shorter than the others, but it's all work. I mean, there's not verbiage in front. It's entitled Thermal Energy. Who's that? Okay, we will be in the lab down the hall, 253, just the very next lab, unless there's a class in there. Now, there hasn't been all term, so I'd be surprised if there was. But that's where we're going to head as soon as I can get things shut down. So, let me close things out. I'm going to put pause. Okay, this is the lab. Each of the teams has in front of you 4 cups. 2 have thermometers in them, cups 1 and 2. Measure the temperatures of the 2 half-filled cups of water. Okay, be sure you keep the base of the thermometer in the water while you're measuring the temperature. Record those temperatures on your lab sheet. Okay? Y'all got them? Okay. Now, pour either one of those cups into the other. If you recorded the temperature, pour them into the other and then measure the temperature of the mixture. You can go either way you want to. Just try not to spill. And you can use either thermometer you want to. Just try not to spill. Yeah, pour all the water from cup 1 to 2 or 2 to 1. That's fine. Pour all of it in there. And then measure the temperature of that mixture once it comes to an equilibrium, you might say. Okay? You got the mixture, the temperature of the mix. Okay? Now, if you got cups covering, measure the temperature of the cups 3 and 4. Okay? Measure the temperature of the cups 3 and 4. Okay? You got 2 thermometers, use the button. Move the one from one. Yeah, good. Okay. Now wait, don't mix. Yeah, 3 and 4. What thermometer? Oh, you got okay. Okay, yeah. Measure the mix of temperature of mix 1 before you move your thermometers, and then go 3 and 4. Okay, once you got those temperatures, before you mix anything, estimate what temperature you think the second mixture is going to be. Look at the temperatures of 1 and 2 and 3 and 4. Estimate what you think the mix 2 will be. Okay? Once you've made your estimates, let me know. Let me take a look. Oh, I see. Okay. All right. Okay. Then pour and mix. Ink running out? Or did it get wet?
It's Yes, I think so.
Tristan, if you need a pencil, this one sometimes works. I think my lead's getting very, very short. Yeah, I'm not sure it's going to work. Yeah, I can get it to work. Okay, once you've made your estimate, then pour the other mix and see what your temperature is. Already done that? Okay. Once you've made your estimate, then mix and read what the actual temperature is. Okay, you got it? All right. Now the question is, I'm making an assumption here, were your answers on A and C pretty close to each other?
Yes.
Okay. But did your mixtures, were they very close to each other? Not as close? The answer to that, since they aren't, answer why. Why do you think, even though the temperatures of 1 and 2 and 3 and 4 were pretty close to each other, why mix 1 was not close to mix 2, or as close? Any ideas? No, I just ran out of cups. What's that? Okay, there was different amounts of water in the cups. If you noticed that when you were doing it, so that's why important to notice things in lab. Okay. There were different amounts of water in the cups, so you don't just average temperature, you have to take into account the mass and other things like this. Remember in class, we talked about that. All right, now, next part. All right. We got only 2 scales, but we got 3 teams, so we're just going to have to share a little bit. And meanwhile, no. Okay. I need to go get me some more water. I'll be right back.
More to me. Leave the lid out.
I don't want numbered cups, so you can have.
Yay!
Oh. Yeah, okay.
I can have this.
I don't want a numbered cup. Okay.
I know.
Now, maybe I need some people helping haul if you could.
Man, like you are. That makes it even worse that he's saying it.
I know.
Are we supposed to go up there? She only get more water. He took Lacey and that still. You know you can hear the ocean doing this. Try to hit me. Oh, we're gonna hit you. What are we trying to do? Put the cup back up here and stand with your back to me. No. I don't trust you at all. You don't pump the cup. This. How much you think this was?
Go get the scales.
Scales out.
I took my boys the other night. I said, fellas, man, we'll start cutting that grain a little bit closer.
Okay.
Last day of class, I'm the founder for you. Let us have a look. I said, last day of class, you about to stay up on the cup? Yeah.
not red Solo cups. Okay. Whatever that means. Okay.
Hey, the good ones are white styrofoam anyway.
Oh, yeah.
No, that's the ball.
You can put a little on. Hey,
All right.
still my good.
That was the cup we just brought. Oh, here. Okay.
Spell it now.
Now, the two that just came in, I guess what you better do is get with one of the two, three seated.
I was actually.
Okay. So, two teams have three now and two have two. One has two. So, did y'all all have your labs, right?
All of us have three.
All right.
You got two.
You got it. Got it. All right. What we're doing now is part 2, which is calorimetry. All right. What I want you to do first, and y'all have to share the scales here. Put an empty styrofoam cup on the scale. Okay. You got one. Okay. You got one.
Did you zero these?
Yeah, 0 first, and then put it on. Zero first, and put it on. Okay.
Phil, that's zero.
Wait. No, I'm sorry. Wait. Take that back. Okay. Put the empty styrofoam cup on the scale, then 0 the scale. Okay.
We got the drop down, coach.
Huh? Okay. Now.
Got zero.
Now, pour about half of that water into the cup. Yeah. Okay. Have you zeroed your scale?
Yes.
You got the hot water?
Yes.
Pour about half of that into the cup. Okay. As soon as you are through, take yours off so the
A little bit
next
more.
team can do it. Huh? No, that's fine.
That's good.
Take it off, put it up on that. Okay. Take it off so the next team can do
I
it.
don't need to put the measurement.
No, not yet. No. Okay. You're easy or you still got a little water on it. Okay.
I'm gonna do the measurement.
Okay. Now, for those two that measured theirs already, put your thermometer, one of your thermometers in the cup and measure the temperature of that water.
It's already put it in.
Yeah. So take a thermometer and measure the temperature. Okay? Yeah. Take that and put about half of the water into there. May still be climbing.
Half,
No, the mass of the water.
40.
When you had it on the scale, what was the mass of the water?
Actually, did I need to know that mass?
That's why we had it on the scale. Okay. As soon as he's through, then you do. Did y'all measure your mass? Okay, good. Before you put them on.
The measurement of the temperature is, let me give you this. It's 43. Temperature is 43 Celsius.
Okay? Now, y'all are a little ahead because you don't have to share. Okay, put another styrofoam cup on the scale. An empty one, yeah. No. Take that one
Our
off.
mass of the water is,
Put that on the scale.
the mass of the
Yeah.
water would be.
And let me,
Zero on the scale.
okay, 0 at the scale.
Zero.
Gracious.
Yes, sir.
Not the best thing to use for it, but maybe. Now, I want you to measure a bit of ice. Now, how much water did you have? Fill that, all this, okay? I would say put at least 30 to 50 grams into this cup.
ice here, my God.
Okay, did y'all get your master
We
water?
got the last water, I got 40, it was
Okay, then bring a cup of, or put another cup on the scale.
We're supposed to know the temperature of it too.
Yeah. Y'all get 30 to 50. Okay.
We do have to settle that.
Okay, have you zeroed it?
It is 0, yes, sir.
Okay. Now put, how much water did you have? What was your master water?
142 grams.
Okay, I'd say put 30 to 50 grams of ice into the water, into the cup. Y'all get an empty cup? You have one?
I'm believe it. I'm used to this. I've done this so many times. 30 to 50.
Yeah, somewhere in that range.
That's 40 grams.
That sounds great.
40 grams of ice in the cup.
Okay,
I'm right on 40 grams.
take it off and pour it, put the ice into the water.
Exactly.
Take the ice and put it into the hot water you
40
just
grams.
mixed. Take that water, yeah, take that ice and put it into there.
Just have a couple
Take
of
the thermometer out for now. Dump the ice in it and leave the cup over the top.
You just want to cover it up once we pour the ice in it.
Yeah, with that cup, yeah. Put it in slowly. Okay. Now, I meant to say don't pour it all at once, okay, but I was too late for that. Okay. 0, put 30 to 50. How much ice water did y'all have?
Even it up
Wait.
a little bit. Gotta even it up a little bit. I smell
Yes,
something.
yes.
331.
Well, I'm not sure I've cleaned that one. But
No, don't worry. No.
331. Wow, okay.
Not
30
big
to
inch.
50.
That's why it's about 2 days.
Put about half on, right? Okay.
Put the thermometer back
30
in
to
now.
50, yeah. Well, did all the ice melt?
Yeah, she said she.
Yeah, 30 to 50.
She said
You
she.
did? Okay, then put the thermometer back in. You got 30 to 50? Okay, record the mass and pour it into your water. Once you recorded the mass, cover it, and then check it periodically to see when all the ice melts.
All the ice is gone.
Okay, then measure the temperature of the mixture. The one that you measured. You know, the mass and the temperature.
Temperature of ice.
Okay, this is the cup over the bottom. Yeah, hang on.
20.
Now, now. Okay, y'all check the ice and see if it melted yet. All the ice melted? Huh? Then, okay, then measure the temperature of the cooled water.
That'd be the maximum.
That's number D.
I
Huh?
got 21 degrees.
Oh, okay. My dad used to say that must be an intelligent conversation.
21 degrees Celsius. Dr. Powell.
What?
21 degrees Celsius.
Don't forget, put it down. Okay, now,
Put the top, put the cover back on.
no, it's not necessary. You got the temperatures you need. Okay. Do any of you remember what equation? Okay, now we're let's finish this. Okay. Now we're going to have to make some calculations now.
Okay.
Here's what we're trying to do. We're trying to measure the heat loss. What lost heat in this problem?
Water.
That first thing of water you had, right? How do you measure how much heat it lost? What equation would you use? Equal,
M.
right? Was there any latent heat in this one? That water? No.
You just subtract.
You didn't steam the water or you didn't melt or freeze the water, so there's no latent heat here.
Shouldn't you just subtract how much temperature was by how much
Okay, that's
temperature?
temperature, that's not heat. No, we need that degrees Celsius. Huh? Okay, let me go get a marker because it looks like I'm on need one.
No, you said, oh, you said June.
June
June
times-
times Q minus.
Yeah.
Shit, now you Q times.
Hey, what's up, buddy?
J times Q equals W minus U two minus
Okay.
U one.
I have a question. I realize those are letters, not numbers yet.
Oh my god, you're
I'm
sorry.
messing with you, man. I'm sorry.
Come whoop his ass.
Not today.
Come on, try to line the foot.
Let me ask again.
Ask me again.
Okay.
Just ask Tracy. No,
What?
no, just ask him.
What changed between that warm water you started with and the water at the end?
You add a couple.
Okay, yeah, I know. You added ice to it.
Times Celsius.
But what measured?
Calories.
Second, okay, what measurement did you notice that changed?
The
The temperature. Now, what equation do you use for a change of temperature?
U equals mass.
MC.
MC delta T.
And this is heat loss is equal to
MC
MC
delta T.
delta T. Okay. Now, what was the mass? Now, this was the original water. What was its mass? Each team has a different number. And that was in grams, right? Okay. What C would you use in that case? What does C stand for anyway?
Calories.
No, it doesn't. CAL is calorie.
Oh.
C stands for?
Celsius.
No, that's degrees Celsius. Capital C. This is a part of an equation. This is a parameter,
Ice.
not a unit.
Ice. Come on.
Okay. What did we talk about? Okay. Temperature is T.
C.
Weight.
No, that's mass is M. That's not weight, but it's mass. What does C stand for? We talked about it. When you have a change of temperature, what quantity do you use? When you have a change of phase, what quantity do you use? Someone was starting to give it to me a minute ago. Huh? Okay, that's a unit. But what is it you're measuring? Huh? Specific heat. C is your specific heat. And what was that of? Water. What's the specific heat of water? 1.00, but it has units.
Calories
Calories.
per gram Celsius.
Okay, so this was whatever your mass was in calories, in grams, times 1.00 calories per gram degree Celsius. And what was your change of temperature of that water?
It was from it went from 42. We had 42 to 21.
Okay, whatever that change of temperature was.
Give me numbers.
Can y'all do the difference? Each team has a different number. That's why I can't write it on the board. Say again? What would you change your temperature? Each team has to answer for yourself. You got what it is? Huh? Yeah, the original water to the final water. The final water was at one temperature, the original water at another. That should change your temperature. Okay, you're not measuring. Okay. No, that's grams of ice. Your water was. Be sure you use the mass of the water, not the mass of the ice. We're losing heat of that warm water. That's the mass you use. See, we know what it is. What was your change of temperature? You have to make your subtraction there. What was it? Okay. All right. Change your temperature. Ended up at 22. What did it start at? Down here, calorimeter.
Oh, 40.
Yeah,
242.
that should change the temperature.
242
We're not using
22.
any of the data from the previous experiment. This is part 2,
It'll be 18.
18. So that's your delta T. Different teams will have different mass. You have different masses. Everybody uses the same C. Calculate your delta T. Do you know what that is? Have you calculated it?
I'm trying to get it. We got 242 times everybody's C is the same,
Okay.
which is
What should change your temperature?
22.
Where do you get that?
We get 43 from 21.
Okay. Sure enough, that's 22.
So,
Okay.
he said, what's the same?
Cause I was
Where
42.
did you start? It's about 42.
Right.
And you ended up at
331.
Times
what's the difference? Delta. Difference, yeah.
Tell me about the C though.
Oh, C.
Yeah, what is C?
Okay. What was C? Someone answered it. You answered it.
The specific
I got C.
The specific heat.
Specific heat. And what is it for water? He answered
1.0.
that.
1.00.
And what unit? Calories per gram degree Celsius. Okay? Actually, the units there are the most important part, but one is just not. Okay?
242 times 1.0. 242.
And what would that be? Whoa.
Let's say calories per what?
Calories per gram degree Celsius.
You said 242
Yeah.
times
Times what?
1.00
1.00
times
Right.
22
Equal.
equals.
Different number than you showed me before.
Yes, it
Okay.
is.
What is that?
532.
5,324. This is for this team only. And what units?
That would be in calories, gram.
Now, that specific heat is calories per gram degree, but you multiplied it by gram, and that was your mass, so it wiped out the grams. You multiply it by change of temperature in degrees Celsius. It's calories, exactly. Heat is measured in calories.
5,324.
Okay. Did y'all get a number similar to that?
4,950.
Sounds reasonable. Calories. It's C-A-L. Capital C is Celsius. Y'all went to that?
C.
Y'all get a number? Not yet.
Okay, so your equation.
Okay, wait one, we'll wait till they finish and we'll go. Well, we could be started on that. Okay. Now, that was your heat loss. You started with warm water, you wound up with cooler water. Obviously, that warm water lost heat. Now, what gained heat in this experiment here? Okay, what happened to the ice? It melted. That was one gain. Okay? So we have the Q gain from melting. Now, what formula do we use for that?
What again? Wait a minute. Can you say that question again?
Okay? The heat that you gain from melting, the ice gained from melting the ice. So that's the first thing you did to it. What formula is that?
Okay, so that would be Q equals
Equal what?
UC.
No. There's no change of temperature here. We're not using specific heat. We're melting the ice.
Melting point would be M L
Okay, M, L, which one?
V.
L, fusion. Think of it as freezing. It's not freezing, it's melting. And what is your mass of the ice now, not the water, mass of the ice? This is mass of water. Second, whatever yours was. And what's the latent heat of fusion for yours? The specific heat was here 1.00 calories per gram degree Celsius. What's the latent heat of fusion for water? Ice to water, water to ice. Whoa, where did you get that?
No. Fusion for water 80.
80. What unit?
80.0.
80.0 calories per gram. Notice you don't have any delta T degrees Celsius because there is no change of temperature when you melted the water. Melted the ice. Later you warmed that, but now you're just melting it. So it's the mass of the ice times your 80. And each one of you have a different mass of ice, so you multiply that out and see what you get. And what units will it be? All right, that seems reasonable.
That'd be calories. It'd be units to be cal.
Yeah, that sounds reasonable. Okay, you haven't done the melting, or have you? Oh, yeah. You have this one. Okay, that seems reasonable. All right, and what's the last thing that you did to warm? When you melted the ice, okay, y'all listening? When you melted that ice, whatever mass of ice you had, it melted and became water with that same mass, right? But what temperature is it now? Right when it melted?
21. No.
When it melted, it was at 0.
0.
Then it warmed to 20, 21, whatever it was. So the second thing you did here to gain heat was warming the ice water. Okay? Not the original water, that ice water. That ice melted, became water, and then you warmed it. What formula would you use for that? M.
L.
Okay? What L are you using here?
We're not using it.
Not using an L. There's no change of phase. What have you got? A change of temperature. To a change of temperature, we use what?
Delta T.
Say?
T.
C.
C.
Delta T. You have to have a change of temperature, so you use the C. Now, what C is that? Now, what M is this? Mass of the ice. That's what's warming from 0 to wherever it's going. What C do we use? Water. And that is the same as here. Calorie per gram degree Celsius. And what is the change of temperature of that ice? We'll assume it started at 0 and went to whatever your final temperature was.
M is the mass of water multiplied by the constant, which is
Yep.
whatever the 1.00 is.
Times the change of
Yeah.
Times the constant
It is what it is.
that
Huh?
is the delta T.
The difference between, okay, notice here, assume that it started at 0 degrees Celsius. So it goes to 0
Water times
1.00 grams.
times 1.
That's the constant. And then for mass, whatever mass of ice that was. And then the delta T would be 22.
Yeah. But your C, you're not using this C, you're using this C.
Yeah, we use it.
Okay?
That would be addressed in calories, correct?
In calories. Okay. Now, what you have to do now is add your two heat gains. The one from F and the one from G. 2 calories that you have there. Not your heat loss, the heat gain. One was from melting and one was from warming. How did you get that?
Do we not multiply or mass
Of what?
of water?
No. Ice.
Oh.
He's funny.
Okay. There's what it is. Okay. Now, you got your total heat gain recorded, except for that thing. Okay. Now look at them and see what the difference between your heat loss and your total heat gain is. the difference. Take the big one, subtract the smaller from it, and write your difference down there. What did it come up with?
5,000.
Okay, good deal. Yeah, excellent.
And then to get that,
Okay. The difference is the difference between this one and this. Heat gain and heat loss.
What's the numbers?
3200.
Plus
Do your difference.
57, 72.
Yeah.
7240, that goes in the difference.
What's that?
Okay, the loss will go in the difference. We say subtract the gain and the heat loss.
Right. How did you get?
We got 7240.
How did you get that?
3200.
You add these together, get your total heat gain.
Okay.
This is your heat loss. The difference between those two.
So we do 5224. 5253.
Yes, sir. Okay. We just do our research. Heat gain, heat loss. Heat gain. Yeah, that looks good. And, sorry, no, do it.
stop.
Yeah.
Are we subtracting these two right here?
Yeah.
This one and this one?
Yeah.
Okay.
Now, how did you get this number? Where did you get it? No, it doesn't. Oh, wait. Oh, I'm sorry. How much ice? 40 times 21 is, huh? 21. So let me see you do that. 40 times 21.
40 times 21.
840. You got it. Much bigger.
So now we say,
Okay. Now,
now we say
what I want y'all to do,
5,
okay,
22, minus
really good.
44.
Let's
I think
go.
it was 1284.
150, divide that by 5100.
Right. Now it says subtract those two.
4,000.
About 3% error. That is really good. Anything 15% would be okay. 3% would be good. So it's going to be hard to say
So now
why
we're going
the odds are
measurement
any little thing you make a difference there.
from
You have more heat gain.
53, we give you 1284.
I'm typing in the right thing.
I'm guessing.
I'm like keeping your number in my head because I don't. Yeah, because I don't have to do it. I just do it because I'm weird. I'm paranoid. I have to go over.
It's going to be hard to say. It's so close. It's not, that's a negligible difference. You can just put it there because yours is really close. Well, look at our equipment here. Styrofoam cups and old thermometers. Yeah.
Efficient number.
Yeah, really close. 15%, and with these conditions, that'd be okay.
What should
Y'all
be
are
under ideal?
Heat loss is 53.
Yeah, 3% would be good under ideal conditions. I like it when it's 5,
How do you spell nigga?
now, what I want you to do.
Hey,
this
you can say
number
that.
divided by that equals what percentage error. Just go to the measurements. One, two, four, two,
Why is the heat loss?
divided by 62. You got about 20% error. That's a little on the high side, but what you have, that's okay. You don't have to write it down. Which is larger, your heat loss. Well, here was your heat loss. The odds are this room is much less than 23 Celsius. 20 Celsius would be 70 degrees. 23 Celsius is even warmer than that. So you've lost a lot of heat to the room. Up heat, that's what you want. lost heat to the roof. Okay? Now, what you gonna find tonight? Okay, so I would say put he lost. Okay, now that's one. Okay, no. Put arguably he lost. Okay, now what you want you to do then? No, yeah. Well, just say he lost. Now take this number and divide it by that number. Divide it by 53. Pretty high, but it's okay. And why? Okay, here's the why. Okay. Here's the why. This temperature is pretty much above what the room is. The room right now is sitting at 68 degrees. Okay, 21 degrees Celsius is probably 72 degrees. So pretty close to it. So therefore, the odds are you lost some heat to the room. Because when you had the cup uncovered, it was losing heat. So, lost some to the room. Okay. One team had just a little more heat gain, but their difference was so small, it was negligible. Okay. Now, there's one last part to the lab. Does this make any sense? Have you got any questions so far? Okay. The last part is conduction. And if you come over here and only 4 people can do it at a time, but everybody can do it. Okay? What you'll find here is a plastic device and a metal device. Okay? It says first, estimate the temperature of the metal and the plastic. And I'll just tell you this. They've been sitting in this room for hours. Okay, since before class began. So they've been sitting in here a long time. What would you guess the temperatures to be? Really? All right. They've been sitting in the room. Okay? Not yet. I mean, we're not getting there yet. They're at the same temperature. They've been in the room. There's no reason for them not to be at 68 degrees. I haven't had them in any hot water, any ice, or anything else. They're both at 68 degrees. Because the room's at 68 degrees. So you can fill it in. 68 degrees. Now be sure to put Fahrenheit. This is Fahrenheit temperature here. For both the metal and the plastic. They've been sitting here in the room, and actually they've been in the building for years. Okay, they haven't been outside. Okay, then what I want you to do, hold one each to your cheek, now facial cheeks, okay, and okay, and see which one feels warmer. Everybody can come do it.
Zach, don't count. Got too much of this.
Okay, one metal, one plastic. See which feels warmer. That's what he thinks. Okay, you see it. Very good. Okay.
Just the metal feels good.
I'll express it a little bit differently, but that is absolutely correct. Touch one each. Huh? Plastic feels warmer? Oh, feel on the cheek. Okay, which feels warmer? Yeah, which feels warmer? Okay, plastic. Okay. Now, Zach had a good explanation of this. Let me explain it a little bit differently, but basically saying the same thing. And by the way, have you answered the second part? And by the way, let's not be playing with thermometers. Okay. Especially these that contain mercury.
safety video, it actually showed you starting.
Okay. All right. Did everybody answer the C part on 4C? Did everybody answer the 4C part?
Yes.
Okay, everybody understand? Here's what's going on with that. Okay? Because the metal, and Zach was saying it just right, because the metal is a higher conductor, and the plastic is a very lousy conductor, when you put them against your face, because this isn't conducting heat away, you're feeling something pretty close to your skin temperature, because it's not conducting any heat away. The metal, however, is conducting it away like crazy because it's a better conductor, so you're feeling room temperature. This is feeling very close to 68. This is feeling probably 90 or so, because it really rapidly comes right up to your skin temperature, because that's what it does. It doesn't conduct it away. So you're feeling 90 here, 68 there. That felt like a big difference, didn't it?
Yeah.
Okay. Make sense? All right. Now, technically, you have until a week from Thursday, after Thanksgiving, to turn these in. If you're through with them tonight, I can take them tonight. Okay? Did it make sense? Did you have any questions? Okay. Okay. Did you feel like the lab was worthwhile?
Yes.
Huh?
Truly.
Truly. Oh, that's nice. Okay, you ready to do the test? How many of you want to take the test tonight?
Would you mind if I took it next class?
That'll be fine.
Thank you.
Okay. Actually, we'll have the other tests in too.
Yeah,
Other one than do that. Okay. So how many need to take test 3?
No, I'm not gonna.
2? How many need to take test 3? Okay.
I need to take test 3.
You do. Okay. There's 3 of you.
Yes.
If you want to go to the classroom, you can. It's a lot more comfortable than sitting on stools. Okay. Okay. You want pen and pencil? Actually, there's a pencil on the desk in the classroom. What's that? I can. Yeah. Or if you want to, yeah, dump it into the sink. Minimize the spilling. Be sure to take the plug out. Yeah, everybody have a good, as you said, safe Thanksgiving. You too, thank you. Y'all get the whole week off. We only get 2 days.
I might go to work.
Oh, okay. Enjoy.
Well, I'm gonna enjoy my face. I have to work, but oh, we get to enjoy the Iron Ball too.
That's right.
Ooh, look at some party in this weekend.
Especially when Bama gets her shit on.
Ooh, that thing gonna go down. Let me make sure I got my. You want
Thing
some Iron
is-
Ball, Dr. Sal?
We probably will. My wife went to Alabama, so.
Uh-oh.
But her sister and her niece goes to her sister went to Auburn, her niece goes to Auburn. So but I still would like to see Alabama come out and see this. What's that?
Test on chapter 4 when we get back, right?
Yeah, test of chapter 4 when we get back.
Got it? Take your time.
You done book bags over me, or you got some in your pocket.
Now, where you park? Some park right over there.
I'm part on,
Other side.
close to the cafeteria.
Dr. Fowler, I'm gonna walk.
Yes, absolutely. Y'all have a good, thank you. Thank you. I'm gonna turn off screencast-o-matic.